Odyssey canister recording data has started. No UHF signal is expected yet.
We've now confirmed that the data stream that will contain the Phoenix transmissions is flowing to Earth property from Mars Odyssey. All we're waiting on now is cruise stage separation and UHF on.
Attention all stations, Mars Core, this is Phoenix Ace. Both Station 14 and 26 report LOS on X-band downlink.
And all stations, Phoenix Systems on Mars Core, the DSN is lost X-band, indicating expected cruise stage set.
Confirmed cruise stage separation, we have acquired a UHF signal. We're standing by for completion of turn to entry.
Phoenix is successfully separated from the cruise stage, which was no longer needed. This cruise stage will just burn up in the atmosphere. We have now started our UHF transmissions and have been picked up on Mars Odyssey to confirm proper separation.
Transition to 8K data. 3 minutes and 50 seconds. All Phoenix stations, EDL calm at this time. Please perform a LAD flush and a red alarm update. All stations, Phoenix now 2 minutes past cruise stage separation. At this point in time, we have a signal via Odyssey and direct to Earth. Standing by for Phoenix transition to 8K data in 2 minutes and 47 seconds. All stations at this point in time, we completed step 2.9-74.
At this time, Phoenix is waiting to enter the atmosphere. We can see very clearly here the UHF communications are strong between Phoenix and Mars Odyssey and to the Earth. We've got a good carrier signal, as you can see on the Doppler plot. Give a little view here in the visualization of that geometry. You can see Mars Odyssey on its trajectory almost perpendicular to the spacecraft at this time, and almost directly out of the back of the vehicle is the Earth link, both of which are being recorded here in real time. Pretty soon, Mars Reconnaissance Orbiter will also be in view, and at that time we'll establish a link with them as well. They are recording it as we speak, and very shortly they will be in a position where they can record the signal directly from the lander as well. You can see here the trajectory that Phoenix is expected to follow. Coming up shortly after entry, we will start seriously decelerating in the atmosphere. And you can see that in the trajectory path here as the predicts show the bending of the trajectory as it
Phoenix now
turns
4
toward
minutes
the surface.
past cruise stage separation. At this point,
We can see MRO should now have a good signal as well
direct to Earth
in their recordings.
Phoenix transition to 8K in 47
And you can see
seconds.
how Odyssey and MRO both are converging over the lander as we get closer to parachute deployment.
Expected switch to Phoenix 8K data in 10 seconds.
All stations, MRO sit on Phoenix test. At this time, we can confirm MRO DSN expand LOS due to MRO relative flu as expected.
All stations, Phoenix switch to 8K detected. Standing by for atmospheric entry in 1 minute and 35 seconds.
At this time, Phoenix has now started transmitting 8 kilobit per second data as opposed to carrier. Originally, carrier, like we said before, was like a constant C note that was just easy to pick out. We are now transmitting actual data. That data is being received and recorded and will be played back later. The turn to entry has been completed, and now all we're waiting is the entry to the atmosphere. You can see in this view the communications links from Phoenix to the two orbiters. They're both very strong and getting stronger. MRO and Odyssey, like I mentioned before, are both converging over the top of Phoenix toward parachute deployment. We're getting very close to entry.
Atmospheric entry on my mark. 5, 4, 3, 2, 1, mark. Expected peak heating rate in 1 minute and 40 seconds. Standing by for a possible plasma blackout.
We have now entered the atmosphere and are starting to slow down. As the atmosphere gets thicker and thicker, the heat shield will get hotter and hotter and start to ablate. When that happens, we'll be generating a local plasma, and that may affect UHF transmissions. We may see some blackouts occur in this time frame.
Phoenix now 1 minute past the entry point. We still have a signal via Odyssey. And we see it on direct to Earth as well. At this point in time, we notice a drop in the Odyssey signal, but we still have Odyssey data. Okay. At this point in time, Phoenix goes normally through peak heating. At this time, we still see a signal by Odyssey. Phoenix now 2 minutes and 25 seconds past the entry point. We still have a signal via Odyssey. Standing by for reacquisition via direct to Earth. Standing by for Odyssey switch to 32K in 45 seconds.
We've been maintaining Doppler lock with Mars Odyssey all the way through the peak heating point. Peak heating is where we would have expected to lose the signal. We've maintained it all the way through. At this point, we've also experienced the maximum G forces that we would have experienced during re-entry at about 9 Gs.
Stop of Odyssey canister data and switch to 32K in 10 seconds. Odyssey switch to 32K detected. We have Odyssey locked up onto Phoenix carrier. Standing by for expected parachute deployment, and Phoenix switch to 32K. At this point in time, Phoenix would have normally deployed its parachute, standing by for telemetry acquisition. Phoenix switch to 32K detected. We have data lockup, parachute deployment trigger detected, heat shield trigger detected, ground relative velocity 90 meters per second. Ground relative velocity 80 meters per second. At this point in time, standing by for radar RF on and altitude convergence. Radar switch to altitude mode. Standing by for altitude convergence. Land leg deployment trigger detected. Ground relative velocity 60 meters per second. Standing by for altitude convergence. At this point in time, Phoenix would have normally reached altitude convergence. We're standing by for confirmation via telemetry. Radar reliable. Altitude 2,000 meters. Altitude convergence detected. Altitude 1,800 meters, 1,700 meters, 1,600 meters. Standing by for lander separation, altitude 1,100 meters. Signal may drop out during lander separation. Altitude 1,000 meters. Lander separation detected. We have reacquired the signal. Gravity turn detected. Altitude 600 meters, 500 meters, 400 meters, 250 meters, 150 meters, 100 meters, 80 meters, 50 meters. Constant velocity phase detected. Altitude 40 meters, 30 meters, 27 meters, 20 meters, 50 meters. Standing by for touchdown. Touchdown signal detected. Landing sequence initiated. Helium vent detected. Standing by for normal termination of EDL comm. Standing by for nominal termination of EDL comm. We have nominal termination of EDL comm by Odyssey and direct to Earth. Phoenix has landed. Phoenix has landed. Welcome to the northern plains of Mars.
Well, the Phoenix has landed. We've just witnessed quite a dramatic moment here. 7 very anxious minutes of EDL followed by a spontaneous outburst of celebration when the team received verification that Phoenix is on the ground, apparently safe, given what we know at present. With me right now is Barry Goldstein, the project manager. So tell me about this.
In my dreams, it couldn't have gone as perfectly as it went tonight. It went
Absolutely.
Right down the middle. Absolutely perfect, right down the middle. We're on the surface. We had a minute worth of data after touchdown. We can confirm that we're at 1/4 degree tilt. We're almost dead on our azimuth, which means we're almost pointing perfectly east-west as we expected. We now have, as we speak, as I'm talking now, it's probably done, but actually it was done 15 minutes ago by now. The solar arrays should have been deployed. That's the next critical event. We wait anxiously for Odyssey to pass over here at 6:45 local time. It'll take about 15 minutes, and we should get confirmation that the solar arrays are deployed. But now that we know we're so flat, it's hard to fathom we'll not be able to open at least one of the arrays.
Could it have possibly gone any better?
Not in my dreams. I'm in shock.
I have
we
to
had
say,
all the signals, everything. Just as we could have scripted it, we rehearsed all the failure cases. Never did it even in rehearsal go this well.
but we can't quite do the high fives just yet, though, right?
No, not just yet. We have to wait for the solar arrays to deploy. But frankly, this was by far the hardest part. And as we've said for the past few days, we have contingencies and multiple tries for the solar arrays. EDL, it's got to go, and it's got to go on time. So
I did catch you tearing up a couple of pieces of paper there. What was that all about?
Well, there were a bunch of contingencies that we had to go through, and I was joking with Blaine that we tear them up one at a time, and he saved a bunch of them for me for after landing, and I tore them up here through, and I'm speechless.
It must be a huge relief after so much testing and
5 years. It is.
And that you know, you exhausted all the possibilities, you tested everything, you left no stone unturned, but you never knew for sure.
Yeah, we never knew for sure. You know, we have the best team, the absolute best team in the world, between the guys at Lockheed, the guys at JPL, the team at Langley, all the support we had from Ames, all over the country and all over the world. We just had the best support, and you know, what it goes to show you is you can learn from your mistakes, you can fix things, and you can make them work. And this team proved that, and I can't be more proud of them than I am right now.
All right. Well, Barry, I feel a little guilty keeping you out here.
Yes, please.
I know that folks are in there whipping out their cell phones, calling home and saying, we did it. I know you wanted to be one of them. Back on the interview set, Peter Smith is with us. Peter is the principal investigator of the mission and the mission lead. Peter, you have always been optimistic, always positive, and
I was right.
Yeah, you were right.
I was right to be optimistic. This team performed perfectly. They couldn't have done a better job. Did you see that thing zoom down and just touch? Perfect.
You have to tell me what that was like for you.
What it's like for me?
Yes.
Well, I couldn't let go of the chair there. I had a grip on it, you know, because I think I would have fallen over without doing that. And anyway, it was just a thrill. And I want to say hello to my friends and family down at the U of A who are all watching. And by God, we're bringing that mission back to Tucson tomorrow.
And there we have it. That's the U of A. They see themselves. There you go.
Hi, guys.
Tell me about this. This project will move into their hands pretty soon.
I think they're ready. Don't they look ready?
Yes,
I mean, actually,
tell us about that.
Look a little tipsy down there, but
but they'll be taking care of the surface operations.
They will start surface operations right away. We get that first picture, and we'll start planning what to do next. So, hour and a half we have to wait. I know it's a long time. It seems like it, but those pictures are going to be well worth it.
And explain that. It's not over until we know, we have confirmation those solar arrays are deployed.
We have to make sure the spacecraft is healthy. But by gosh, it has landed in a place where it's just almost horizontal to the surface, tilted 1/4 of a degree. So it's not on a rock. It's in a nice flat place, very safe and happy. I just can't imagine the solar arrays won't open.
So looking forward to 90 days of great science?
Great science. And maybe extended mission. Huh?
Think of that.
Where's Doug McQuistion? We need extended mission.
All right. Well, thank you so much. I know you want to go back in there, say hi to everybody, and the folks down in Arizona are ecstatic, I'm sure.
Hello, Arizona.
All right.
Bringing back a great mission. And hello, Europe.
Yeah.
Really, this is a world mission. I don't want to just single out Arizona.
Right.
We really are doing this for everybody.
All right. Well, great day for the Phoenix mission. Let's go back to the control room. We're going to step back and get a bigger picture look at what NASA is doing at Mars. And to help us with that is Doug McQuistion. He is NASA's director of the Mars Exploration Program. I know you're just excited as
Absolutely.
Everyone else. Give us a recap of what it was like in there and how everything just came in just the way you had hoped it would.
I will, absolutely. Well, you know, it's there's been a level of anxiety leading up to this, but frankly, once the EDL sequence started and as soon as we had cruise stage separation, the anxiety level actually kind of took a notch up. People really got uncomfortable. This is where, I mean, this is the defining moment for this project. They spent all these years to enter the atmosphere, and this is also the hardest part. This is where things can go wrong, and so the pucker factor really kind of jumped. But as we saw things tick off, and they ticked off within seconds of when they should have, you know, getting new communications with Odyssey, the orbiter slewing to the right orientation, the cruise stage coming off, switching data rates, just everything, propulsion line, pressurization, everything went just absolutely flawlessly. In fact, some things went better than expected. We expected to have a UHF dropout in the peak heating time frame, and we lost the signal a little bit, but it never went away completely. Odyssey still had communications with it, and so this spacecraft has been a flawless performer since launch. And it continued this all the way to the surface. It was just flawless. It was unbelievable, an unbelievable performance.
So now that we're on the ground, what next? Where to from now?
Well, as we speak, we should be, the spacecraft ought to be deploying solar arrays, if I have my times proper. And we'll have a camera come up, and it'll be going through its own safety and health checks and be actually preparing itself for the Odyssey overflight. So the orbiter Odyssey should be flying over in probably an hour and 20 minutes or so now. And that'll be actually the first landed contact on the surface of Mars for Phoenix.
And in looking at this mission in the context of the overall Mars program, what do we have here? I mean, this is the footsteps for the future.
It is. This is actually, it's not only the footsteps for the future, but I won't say it's the culmination, but it's a major step in our follow the water strategy. Odyssey and Mars Global Surveyor and Mars Reconnaissance Orbiter have given us information to tell us the planet was wet and warm in the past. Mars Exploration Rover Spirit and Opportunity are there, and they have proven that that's true. They have shown us the data in the rocks and the geology of the planet. Phoenix now, to take it a step further, is actually going to go touch that water. It's going to, for the first time, humans will be touching water on another planet. Absolutely exciting. It does set the stage for the rest of the decade. It sets the stage for the next mission, the Mars Science Laboratory, which is a 2,000-pound rover that's full of chemistry instruments, and it will be analyzing different soil types, and it won't be going to the pole, it won't be going to the Arctic, and so it probably won't see ice, but it will sample a lot of materials and help us really understand what Phoenix is going to help us understand on the northern polar regions of the planet.
I just can't help sitting here with you right now, flashing on the statement you had a couple of days ago, quoting a Rolling Stones song about you can't always get what you want.
We did get what we needed.
You did.
We did. Yeah.
And
it's great. It's just exciting. It's
well,
really exciting.
Congratulations.
Thank you very much.
Thank you so much. And you can go back to the celebration.
I will do
Back to Mission Control.
Okay, it's been a historic day for NASA, indeed, for space exploration. Let's go to our Miles O'Brien, who is in Pasadena at Mission Control for the latest attempt on Mars, which, Miles, obviously was successful. It happened just a while ago, and I believe you've got new news for us.
Well, we sure do. Incredible news. Now 2 hours since the Phoenix lander made it to the surface of Mars, just north of the Arctic Circle there in the tundra, and we've gotten our first images back from the surface, and they are quite a sight to see. First of all, they have confirmed that the solar array is deployed. That's extremely important. That was what they were designed to do, take pictures of the solar arrays first. And then they actually have given us a glimpse of the horizon. Steve Squires, who is the principal investigator on the Mars Spirit and Opportunity rovers, watching these pictures with us, explain the significance of these shots as they've come in. Obviously, a lot of excitement in the room there.
The first thing you got to do is make sure your spacecraft is safe. And getting those solar arrays out is absolutely critical. That's getting the vehicle what they call power positive, meaning it's producing more power than it's consuming. Those pictures show the solar arrays are out. That means the vehicle is safe, it's alive, it's got a long, healthy mission ahead of it. So that was the most important thing. Look down at the foot pads, you can see what the terrain is like. The vehicle is totally flat. It's on a beautiful flat plane. And then the best of all was those pictures of the Martian horizon and the terrain in front of it. Doesn't look like anything I've ever seen on Mars before.
Well, this is a whole new Mars for us, isn't it? We have never been here.
Now. Yeah, we're in the Arctic now. It's a totally different Mars, and it's crazy looking. I'm dying to see more pictures because what I just saw was beautiful.
It's more like being in the Northwest Territories or Nunavut or one of these tundra places.
It's something like that. You could see polygons on the ground. You could see these network of fractures on the ground. And the way that happens is if you have ice in the ground, and it gets warmer and colder, it expands and contracts, and it cracks the ground. And I think that may have been what we were seeing there.
And we are certain, pretty certain, based on the information from the Mars Odyssey orbiting spacecraft, that what caused some of those cracks is actually the freezing of water ice. This is the first time a spacecraft will be able to actually touch Martian water in ice form, melt it down, look at it, what's inside. What are we apt to see? I mean, what is it? It's a deep freeze. Who knows what's in there,
it's
right?
Anybody's guess, Miles. Yeah. I mean, this is exploration. You don't know what you're going to get. I think there's a very high probability that they're going to find ice, but the real interesting puzzle is what's in that ice. Or are there organic molecules? in the ice. There could be organic substances in there that could tell us something about whether this soil would be capable at some point in the past or maybe at some point in the future of supporting life. So it's an exciting set of measurements coming up.
I should say, and it's kind of a deep freeze that would capture the remnants of life. You're not going to see living things in ice per se, right?
No, we know that on Earth you have to have liquid water in order for life to exist, and no one expects to see liquid water at these frigid Martian polar temperatures. But what the ice can do is it can trap stuff like bugs in amber, basically, and it can preserve whatever molecules, whatever constituents are there, and it may be one of the best places to go to read a record of what kind of materials are in the Martian soil because it'll be preserved by that ice.
Take a look at the Martian tundra there. That's the first time you'll see it. We'll be getting color pictures soon as the evening progresses, as they have more data passes, communication passes with the orbiting spacecraft. But there you see the first brief images from the Phoenix Mars lander, the footpad on the ground, the solar arrays deployed. Those are the key first steps, and then there's that one shot off to the horizon to give us a little taste of what is to come for this mission, which is it'll be a short mission. It won't be a 4-year mission like yours. We're talking about 90 days, and then it'll pretty much
it might go on beyond 90 days, but when the Martian winter comes, this lander is going to be encased in carbon dioxide snow.
Yeah.
It's all over.
All right. Steve Squires, thanks very much. We're going to continue to watch the situation here at the Jet Propulsion Lab, and as the pictures from Mars come in, we'll share them with you here on CNN. Back to you.
Now, scientists in California may be a step closer to answering that age-old familiar question. Is there life on Mars? Or at least, was there life on Mars? An unmanned NASA space probe has survived a perilous descent to land in the Arctic region of the Red Planet at the end of a 9-month journey from Earth. Later, the craft's robotic arm will burrow beneath the surface to search for the raw ingredients of life preserved in ice. The BBC's Rajesh Merchandani was at NASA's Jet Propulsion Laboratory in Pasadena for the moment of touchdown.
To give you an example, just to illustrate for you, I'm standing in front of a scale model of the Phoenix Mars lander. The real thing right now looks like that. Solar panels deployed, instruments all deployed, and it is operational 400 million miles away on the surface of Mars after an historic and nail-biting landing earlier.
Touchdown signal detected. Landed it.
This was the moment anxious scientists had dreamed of. Confirmation the Phoenix lander had touched down safely on the surface of Mars.
We rehearsed over and over again. We rehearsed all the problems, and none of them occurred. It went perfectly, just the way we designed it.
400 million miles away, it was a perilous descent. Phoenix hit the Martian atmosphere at more than 12,000 miles an hour. In just 7 minutes, friction, a parachute, and then thrusters slowed it to a graceful 5 miles per hour, ready for a soft landing. 2 hours later, Phoenix's first pictures from the surface of Mars. A rocky landscape, and importantly, its own solar panels fully deployed, vital for the science behind this mission. Phoenix is not designed to look for life, rather its potential. The scientific instruments on board will measure whether Mars might once have supported life and whether it could do again in the future. Phoenix will examine the ice scientists believe is under the topsoil. Was it once liquid water? If so, could Mars have once supported life? And could it do so again? This ambitious project has now passed a crucial stage.
This is our beginning. I mean, it's like without the launch, you have no mission. Without the landing, you have no mission. Now we have a mission. It's up to us to make it something wonderful.
Scientists hope to be able to conduct experiments on Mars for as long as 6 months. After that, the planet's extreme conditions will cause the atmosphere on the surface to freeze, and Phoenix with it. Now, let me just give you another illustration of what Phoenix will actually do. See this robotic arm? It extends 2 meters. That will dig down into the topsoil at the North Pole, the polar landing site where Phoenix is, and it'll collect samples of the ice scientists believe is there and analyze it to find out if that ice was ever liquid water. If it was, then scientists believe that that could change our understanding not only of our own planet or our Martian neighbor, but all sorts of planets throughout the universe. Back to you.
Hello and welcome. After a 9-month journey, the Phoenix space probe made a triumphant landing on the northern pole of the planet Mars earlier today. Hitting the red planet's atmosphere at 20,000 kilometers an hour, the probe generated temperatures of 1,400 degrees centigrade. The odds against a tiny spacecraft making a successful descent are slim. For each successful mission to Mars, 2 attempts have failed. Now Phoenix will spend 3 months beaming back information and pictures to a delighted NASA mission control. By examining underground ice, it's hoped the mission will throw light on whether the planet could support life. This report is by Christine McGurty.
20 meters. 50 meters, standing by for touchdown.
At mission control, all they could do was watch and wait.
Touchdown signal detected. Landed it.
This was the moment they'd been hoping for. Confirmation that the Phoenix spacecraft had touched down safely on the surface of Mars.
We rehearsed over and over again. We rehearsed all the problems, and none of them occurred. It went perfectly, just the way we designed them.
After a 9-month journey from Earth, the craft faced a short and perilous descent. Dubbed the 7 minutes of terror, Phoenix plunged through the Martian atmosphere at more than 12,000 miles an hour. First, a parachute slowed it down, and as the 3-legged lander dropped to the ground, thrusters were fired, bringing it to just 5 miles an hour for a soft landing. 2 hours later, the first pictures beamed from the planet's Arctic north, a dry and barren landscape strewn with small stones, and, crucially, evidence the lander's own solar panels successfully deployed, vital to power the robot on its mission. NASA's hunt for extraterrestrial life began more than 30 years ago with the Viking missions. A successful landing, but no evidence of life. More recently, the Spirit rover captured this breathtaking panorama. Several other missions went badly wrong, as did Britain's own effort to get to the surface. So now, after a successful landing, Phoenix can begin its 3-month mission on the surface. No craft has studied this northern part of the red planet before.
This is our beginning. I mean, it's like without the launch, you have no mission. Without the landing, you have no mission. Now we have a mission. It's up to us to make it something wonderful.
The robot will dig beneath the soil, looking for water that's thought to be frozen underground. It'll study the samples for evidence there was ever life here in the past, and whether it might survive somewhere here even now. Christine McGurty, BBC News.
Well, joining us now is Anton Van Plu, who's an astronomer with Planetarium Earth, which is a space and astronomy information service based in the south of England. Anton Van Plu. So, were you excited by all this amazing landing? The pictures are dramatic, aren't they?
I tell you, it couldn't have been better, the whole thing. I mean, everything went totally according to plan. I mean, it was a several $100 million mission, so it had several fail-safes, but nevertheless, it is quite a dramatic and turbulent entry to Mars. So you've got these parachutes, you've got all your thrusters, everything needs to work according to plan, all the altimeters, the things that measure the distance from the planet, and it all worked clockwork. And, you know, we've been looking at Mars over the past we've got several
30 years we've been exploring Mars,
spacecraft flying around Mars, and they've been studying the surface in exquisite detail over the past 5 or 6 years. And this has been the site, the northern hemisphere, that we've heard so much about.
So explain to us then why this Phoenix mission is so important, because we have been looking at Mars for a few decades.
Well, basically, we've sort of dotted missions around Mars, but most of them have been around the sort of equatorial regions of Mars. This is where the solar panels, which are always very important, they're the things that capture the light from the sun and convert it into energy so that the actual equipment can work and the mission can work, have been around the equatorial areas. So further north, you don't get as much sunlight there, but this is where tantalizing evidence is that just underneath the surface is, as we've heard, water ice.
But that's strange. If you say the northern hemisphere doesn't get as much sun, and yet that's the area that you think there might be the strongest likelihood of there having been life.
Well, certainly underneath the surface there's water. The northern hemisphere, it has to be said, is slightly lower It's slightly lower than the southern hemisphere. So you can think of the southern hemisphere as sort of uplands and highlands and mountains. So
we're looking at pictures here actually as you speak. Sorry to interrupt you there. Yeah, I don't think these are from this current mission, are they?
Particular ones
they are from Phoenix?
Are exactly what the scientists believe they would see.
Right.
If you go to the northern hemisphere of the Earth, around the Arctic regions, you find sort of permafrost, and you see these polygon shapes, these sort of large square-shaped areas where underneath the surface water is frozen and then melted again, and you get this patterning on the surface. That's exactly what Odyssey and from the air and Phoenix has found when it landed on the surface. So it's exactly what the scientists believe they would find. So I have no doubt that when they dig just a few 10-20 centimeters beneath the surface, they will uncover the water ice which is down there.
And then that means there might have been life at one time, or there might be the future possibility of life?
Basically, it means the conditions for life are okay. They're not looking for life. They don't expect to find life, but what they do expect...
We all want to find life.
We do,
Mars,
and but we're one step closer to that because we've been studying it, and we are studying it now with the right instruments, the ones that have been taken down with Phoenix. So this is one step along the way. So the next mission that will go, that will be the one which may confirm or deny once and for all that was life there. But this is a very important one for saying, does that ice melt at any stage? Because it's the water that's important for life. There may be ice there, but you need water for life to actually exist.
Anton Van Plu, thank you very much indeed for explaining all that to us. Thanks.
Phoenix ist sicher auf dem Mars gelandet. Sie untersucht erstmals die nördliche Polarregion des Planeten. Ziel der Mission ist es, Spuren von Leben und Wasser zu finden. An dem Projekt ist auch die Europäische Weltraumagentur ESA beteiligt. Die Landung galt als äußerst riskant.
Diese Computeranimation der NASA zeigt, wie die Landung der Sonde Phoenix auf dem roten Planeten ablief. Nach 10 Monaten im All wurde der Sturz der Sonde durch die Atmosphäre des Mars abgebremst. Hierbei schützte der Hitzeschild die Sonde vor dem Verglühen. Ein Fallschirm und zusätzliche Bremsraketen sorgten schließlich für eine weiche Landung auf der Marsoberfläche. 7 Minuten der Angst hatten die Ingenieure der NASA diese kritischen Momente genannt. Als Phoenix heil gelandet war, brach im Kontrollzentrum in Pasadena Jubel aus. In der Vergangenheit hatte die US-Weltraumbehörde viele Marssonden verloren. Es hätte nicht besser laufen können. Wir sind genau an dem Punkt gelandet, den wir anvisiert hatten. Die Sonde ist jetzt auf dem Boden und hat schon 1 Minute lang Daten gesendet. Die ersten Bilder von der Marsoberfläche. Phoenix fotografierte zusätzlich auch seine eigenen Sonnensegel und das Landegeschirr, um zu zeigen, dass die Sonde die Marsoberfläche unbeschadet erreicht hat. Das ist der Traum eines Wissenschaftlers, sagt Peter Smith. Der Leiter des Forschungsteams hält Phoenix für einen Meilenstein. Die Sonde soll mit einer Schaufel Bodenproben entnehmen und auf Spuren organischen Lebens untersuchen. Deshalb wurde Phoenix auch in der Nähe des Nordpols gelandet, wo Wissenschaftler unter der gefrorenen Marsoberfläche Mikroorganismen vermuten.
Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. Well, if you were with us last night, you know that the Mars Phoenix lander had what appeared to be a picture-perfect landing. And today is Sol 1, the first day of surface operations. So we have 2 of the team here to explain to us everything that will be taking place today. First, we have Barry Goldstein. He is the Phoenix project manager from the Jet Propulsion Laboratory. And Peter Smith, the principal investigator from the University of Arizona in Tucson. And we're going to begin with Barry Goldstein.
Thanks, Veronica. First of all, I'd like to thank all of you who stuck out the weekend with us. We really appreciate it. And for the entire Phoenix team, I'd like to let you know that 7 minutes of terror is going to be followed by 3 months of joy. So we really appreciate it. One other comment, one of the press conferences we've had lately, we talked about the first images, those boring pictures that we'd see, those boring engineering pictures. We're tired of seeing solar arrays and things like that. So we figured we'd start this press conference with another boring engineering picture, that's been taken recently, and we can't credit Phoenix for this image. Can I have this picture, please? What you see here I'll put that back up again, please, but what you see here is a spectacular image taken by the MRO orbiter, Mars Reconnaissance Orbiter, by the HiRISE instrument operated by Alfred McEwen at the University of Arizona, of Phoenix on the parachute through its descent phase. You can see the Mars polygonal terrain in the background. The big white, what appears to be white at the top, is the parachute. If you look closely, you can see what look like little white lines going down. Those are the risers from the parachute. The aeroshell holding the lander is actually the smaller white dot at the bottom. Now, this is a very raw image. It's just been taken. There's a lot of work to be done on this. This is going to be much sharper and a much better image once it gets through some image processing, but this is a spectacular image. And speaking for the engineering team, this is equivalent to the first images of landing. This is an engineer's delight. So I know you don't like our engineering images, but we are delighted, and we thought we'd lead off with that. Can I have this animation? We'll give you an idea how this image was taken. What you see here is MRO coming in orbit. The view angle shown by that box is actually the camera angle as well as our UHF radio. And it's following Phoenix into the orbit, and that went very fast, but it fades to our image of the lander coming through the atmosphere. So this was quite an engineering feat. And I have to be frank with everybody here. When this was first proposed, I was very skeptical. I was very skeptical if this was possible or not, and I tipped my hat to the MRO team and all the engineers who convinced me not to talk them out of it. So spectacular image, and I want to congratulate the entire MRO team for pulling this off. It's been wonderful. Okay, now back to surface. We're on the surface now, so we have to operate this mission, as I mentioned before, with UHF-only communications, so we rely strictly on orbital communications. So roll the next video, please. We talked about MRO in orbit. We also have Odyssey as one of our reconnaissance vehicles, and this image shows Odyssey coming overhead. Phoenix turns on its radio, and we communicate back and forth with Odyssey, as we do with MRO. Odyssey also, in turn, communicates back and forth with Earth. So we use effectively a repeater situation here. Overnight, this past evening, or the first planning sol, as we call it, on Mars, we actually validated our communication paths with both Odyssey and MRO. We're very excited to say we've actually established the highest data rates between the two vehicles, which was imperative for us to get the maximum science return. So right now, we've also accomplished our first major goal of the mission, which was to get a command set up to the vehicle. It was radiated up to Odyssey early this morning. Odyssey relayed that back to Phoenix. Phoenix has that in its system, and if I'm not mistaken, right now, as our operations team in Tucson is sleeping, Phoenix is executing that sequence on the surface. So we've achieved our first major goal of the mission, which is establish our two-way communication path with both of our reconnaissance vehicles. So we're very confident that we're going to be able to fulfill all of our goals. Okay, one last thing I'd like to talk about, and if we can roll the last video. You've seen us zoom into our landing site quite a bit, and you recall our landing ellipse. You can see here's the topology map that we've used for quite a while. And we ended up with a 60-kilometer long ellipse as our landing ellipse, and we pinpointed with that red circle where we believe, based on the data that we collected during EDL from our gyros, where we believe Phoenix landed. Well, since then, we've used many of these Odyssey passes and MRO passes to effectively triangulate and really nail down where the vehicle is. And if you put a dot in the center of that circle, the red circle, and move directly due west by 1 kilometer, we now know the position of the vehicle on the surface to a resolution of about 100 meters by 300 meters on the surface. So the reason that's very important is we're passing those parameters up to MRO, such that we can make sure that we get images of the vehicle, of the parachute, of the aeroshell, on the surface, and we should have those for you shortly. And that's all I have to say about the engineering, and at this point I'll turn it over to Peter to show you the really exciting science.
Well, we have the same images this morning we had last night, but we've had a chance to look at them in a little more detail, so it won't be until this evening that we get additional images to show, so bear with us. Patience is required. So let's take a look at the images we have. We've printed our mosaic in color, and let me see the first image, and we'll zoom up. Now down close to the lander, that's about 3.2 meters away, you can see the rocks on the left look like they've been disturbed, and that's likely caused by, and there's some furrows on the right side of this image, likely caused by the thrusters as the spacecraft came down. And now you see these troughs, and from that trough in the front now to the back is about a meter. These are much smaller than the ones we thought we were counting from space, which are more like 5 meters. So, and then there's a density of rocks. We also see what look like cracks in the soil caused by the contraction of ice, and that would mean that the soil is still active because old cracks would have filled in with dust. And there's a couple of rocks on the horizon showing our rock counts were pretty accurate. Those are the kind of rocks in the distance that we would see from high-rise in space on MRO. And so this is our first look at the surface. We've only looked at one tiny little slit of the 360 degrees that's around us. We've looked at about 12 or 14 degrees. So this is, what's that, 1/30th? It's only 1/30th of the scene that we're looking at here. And over the next few days, we'll be filling in the rest of it. Don't be surprised if it looks very similar to this, because that's the terrain we've picked to study, and it's quite likely it'll look the same around. But, of course, until you've actually looked at it, you don't know what's there. And we're particularly interested in seeing what's in our digging area, because that's where we actually can reach out and touch the soil. And speaking of touching the soil in our digging area, we also can look again at our lander foot. And the next slide. This is an animation showing where that lander foot is with respect to the lander. And there it is, and there's our actual picture of it. And we can see, if we zoom in on that with the next slide, we can see that the lander foot there has actually slid a little bit. If you look just above that kind of boxy thing in the middle, you can see the ground has been kind of modified. And it seems like as we came down with a slight horizontal velocity, we slid a little bit on the surface, just a short amount. We can also see that there's a kind of a pebbly surface there, and just to the right of that little boxy thing, it looks like there's been a tiny little excavation of just a little bit, but definitely the soil has been dug into by this lander foot, which is good news for us because we're going to dig into it with our robotic arm. So we're quite enthusiastic to get the rest of our images down, and we'll be doing that later today as we start our mosaic from, well, this will be a single color mosaic starting in the south and working our way around, and we'll get as much as we can down tonight. So it's really good news that Barry's been able to increase our data rate to 128K.
Yeah, I'll take credit for it. Yes, 128K.
You told me you did it, Barry. And so, tomorrow's press conference will be definitely showing new pictures, and as always, as they come down, we're putting them on the web for everybody to see, frame by frame. But the wonderful team here at JPL, led by Eric DeYoung, our co-investigator, really can make some nice products out of those, and so we'll be showing the products. But you'll see the individual frames as they come down this evening over the web pages, and is it on NASA TV, Eric? Yes, on NASA TV. So stay with us. There's a lot of excitement coming, and over the next week we'll have characterized our images, and our characterization period ends and our science mission begins with the delivery of the first surface soil sample to our TIGA instrument. And so we expect that in about a week. So with that, Veronica, I'm done with my presentation.
All right, let's open up for questions. And let me start at the front as usual, and then we'll work our way back. We'll start, well, can we start right here with David Perlman?
Yeah, just two questions for Peter, I think. The very first picture that came down from Viking was a shot of the footpad of the lander, which was, you may recall it or may have seen it. Could you tell me in what order was the footpad picture here? Was it the first, the last, the third, whatever? It's kind of interesting that two footpad pictures 32 years apart were so similar in many ways.
Well, thanks for pointing that out. It's no accident that we took a picture of the footpad.
Yeah.
Remembering the Viking lander's first picture, it was not our first picture because we wanted to be absolutely certain that solar panels were deployed. So those were our first pictures, and those would have come down even if we'd lost communication with the spacecraft and had gone into safe mode. So we had to have those first. As you remember, Viking didn't have solar panels. They didn't have that issue to worry about. They had isotopic
generators.
Radioisotope thermonuclear generators.
And RTGs.
Radioisotope thermonuclear generators, RTGs.
Yeah, there's a lot of syllables there.
Yeah.
Anyway, they they had nuclear devices, and so.
Oh, the other question there that I had was, you talked about tomorrow's press conference. Aren't you going to be in Tucson for that press conference?
Well, through the wonders of technology, we're going to have it both in Tucson and at JPL, and we're going to go back and forth.
Okay.
So this is, I think, a first for us, and we'll see how well it works. But we're encouraged. We've done some testing.
Thanks.
Okay, we'll go over here to Craig Cavalt.
Hi, good morning. Craig Cavalt with Aviation Week. Peter, what day do you expect to be seeing the digging area? Is that early part of this week?
Yeah, that's within the next day or so. We'll start looking at that right away. And there's been a lot of interest, of course, in taking a full set of our multispectral filters in the digging area to try and get some idea of the perhaps color differences and maybe mineral differences in that area.
Okay, thanks. And for Barry, do you know exactly or even approximately what time in the parachute descent phase the image was taken?
I know the MRO team knows exactly what time the image was taken. It was over a short period of time, and what we will be doing is we'll be taking that information along with all the other data that we collected during EDL to help with our reconstruction so we can time its position. We know that the parachute was deployed at approximately somewhere at or below 10,000 meters, and we know that we deployed off of the parachute. The lander deployed off of the parachute at about 1 kilometer, so the image was taken somewhere in that range. So by correlating that with the time and what we are able to then correlate back from the data that we've collected through EDL, we should be able to pinpoint that.
Okay, thank you.
Okay, we're going to go back to Miles O'Brien.
Hey, Peter, do you have any MET data yet? How's the weather on Mars?
The MET data is stored in a storage device on the Canadian side of the payload, and it's downloaded once a day, and that download will happen this evening. So until we get that, we don't know the actual weather. We do know that the spacecraft itself, we know its temperatures, and it's, I think it was minus 33, something like that. Right. Minus 33 is warmer than we expected.
Good.
So we'll have to wait this evening for the actual temperature data of the atmosphere.
Okay. And the Canadians will give you that data. No ITAR issues.
That's right. They're going to put.
I'm curious, Barry, just a little bit about how you set up for a picture like that, because you were on the edge of your 99% oval. I'm not saying you were a bad shot. You still made it, but that camera that was pointing in that direction doesn't have a huge field of view. How were they able to? Was there a little bit of luck in getting that image? In other words.
Well, I won't go with the luck, but what the team did is they basically set the camera. Well, let me take a step back. One advantage we had is that the HiRISE instrument was bore-sighted or pointing in the same direction as its receiving antenna for UHF. So the primary objective for HiRISE was to be able to give us EDL communication. So the fact that the antenna was in the same bore site as the camera allowed us to try to take that image, allowed the MRO team to try to take that image. With regard to us being on the outside of the ellipse, well, first of all, that image was taken, and I'm just going to guess, I'll speculate at the start of the parachute descent phase, but we had very high accuracy of the entry corridor as we were coming closer and closer to the planet, and it was consistent with the information we fed to the MRO team about a week ago. We had a fairly good understanding at that point. So at that point, I think the estimates, Jim, were on the order of 20 to 40% that we would fall within that window. So I guess from that perspective, we were a little bit lucky. It could be that the distribution that put us out on the tail was due to something that happened at that altitude or below. But as I said earlier, we have a lot of data to pour through, and we have a lot of people who are very interested in digging up as to why we ended up on the outside of that ellipse.
I'd like to introduce Jim Erickson, who's here in the front row. He is the project manager for Mars Reconnaissance Orbiter. So I thought I'd give you an opportunity, Jim, if you wanted to add on to any of those answers.
Yeah, I'd probably say that there was an element of luck to it. Like Barry said, it was a 20 to 40% chance. And we made some right choices in how to do this. And Phoenix actually did cooperate, which we appreciate. So this picture really wasn't designed to be media friendly. It was in case we had bad days on Mars, we'd have something that would enable us to figure out what had gone wrong. Now it's going to enable us to figure out better what's gone right, and for the future missions, what we can do to make them even better.
Okay, I promised someone, Irene, I think you're next. And then I'll be going over to the other side of the room again. Right here. There you go.
Thanks. Irene Klotz with Reuters. I have two questions for Peter. The first is, do you have a general idea in terms of cost and complexity, what it saved to be able to use the communications capabilities of the orbiters rather than having a spacecraft or a lander with direct communication?
Well, that might be a better question for Barry. There was definitely a cost savings by not building the antenna to give us the direct-to-Earth ability. My memory is it's somewhere between 5 and 10 million, but I don't know exactly.
Yeah, let me add on to that. That was not our major driver. Originally, we had a direct-to-Earth capability on this vehicle. However, as we were basically finalizing the payload accommodation, or how we laid the pieces of the payload out on the deck, we had a serious concern about mass and accommodations. So early in the mission development, actually in what we call our Phase B, our development phase, we identified that as a potential descope that we could take. And part of what drove that and part of what enabled that was the huge success we had achieved with Mars Exploration Rover on using UHF-only communication. So we went through a very detailed study and several review boards to verify that what we proposed as a way of robustly communicating this vehicle would work. And with the success we had last night, I think we can conclusively say we did the right thing.
Thank you. The other question is about the image last night that had the white thing in the background, if you've had any other opportunity to look at that. And as you get the next opportunity for pictures, are you focusing more on higher resolution images of that same little slit, or are you looking more to expand the view? Thanks.
Our priorities are first to see the entire Martian scene around the lander to give us the sense of place as to where we are, and try and put these few polygons we've been able to see up close into perspective with the rest of the site around us, and also to understand the rock distributions. And I think we'll definitely be getting the highest resolution pictures we can of that feature that we see near the horizon. As you know, these pictures are compressed so that we could get them down the first day, and therefore not our best resolution. So probably towards the end of the week we'll be having better pictures of that feature and have a better sense of the interpretation of what it might be. Okay. Maybe we'll see it from high-rise also, if it's large.
Steve, go ahead.
Last night you were looking out at what some people call the parking lot, and you saw beauty out there. Can you sort of talk about what you see when you see these rocks, what you see below? I mean, you may have these X-ray eyes, what you can see below the rocks?
Below the rocks? Well, my eyes aren't that good, but We noticed that some of the rock patterns don't line up with the polygons. It's like they're remnants of perhaps a more ancient surface. And so that's one thing our science team is considering. As far as knowing what's under the rocks, I'm anxious to find out. We're going to be touching and pushing on them with our robotic arm if we have the opportunity.
But you seem very confident that there's ice below there.
Well, when you look at some of those up-close troughs, you actually see what looks like freshly dug depressions in the center of them. And this is just like the active surfaces you see in the Arctic regions on Earth. So it implies that we have an active surface. In other words, the ice is still there and expanding and contracting with the seasons.
And you talked about this week, the characterization period. Exactly what is taking place now that is getting you ready to start the dig?
Well, our instruments have just undergone a 10-month cruise to Mars, and to help them do that, some of them have covers, some of them have seals that have to be punctured so that they can get into a condition where they can analyze soils. There's a whole set of calibrations that need to take place. In some cases, we have to upload some additional software. So all of this takes some time. We had no idea what the condition of our spacecraft should be, so we gave abundant time for all these processes to take place. The robotic arm, we're dealing with unstowing it from its locked-in position on the deck so it wouldn't be damaged during the landing. And that takes a day or two, and we have to worry about the biobarrier and getting away from that. So all of these things are going to take us a couple of days each one. So when you add them all together, it's about 8 or 9 days.
And let me get one final quick question. The importance of the weather station, how does that help you in the science aspects of this?
Well, the surface doesn't exist in isolation. It interacts with the atmosphere in very complex ways. And we're trying to tease apart the ways that the atmosphere and the surface work together. As you know, there's water vapor in the atmosphere, and it's transported with the seasons back and forth from the polar caps to the equator and back again. So there's water being transported through the atmosphere, and then you have a dry, porous surface where the atmosphere and the water vapor can go in and out of the surface. It actually breathes with the seasons. So the question is, nobody's ever studied exactly how this happens, and we'd like to be able to do that.
We're going to take a question here, and then we're going to take a call on the phone line from Tucson. Go ahead.
Todd Halverson of Florida Today with one and a follow, if I could. First for Barry, you mentioned that you uplinked a command sequence to the lander, and I was wondering if you could go into a little more detail on what's on the agenda for the lander today.
Okay, I can recall part of it. Peter, I think, may have some. One of the things we had originally planned is actually taking on more of an importance today, which was to take more images on the lander deck, particularly around the robotic arm, to make sure we know exactly how the biobarrier deployed. One thing that we noticed from the one image we had yesterday of the deployment, or we actually had two images, but in particular on one of them, is the biobarrier did not deploy 100%. This is of no concern to us relative to getting the arm unstowed, because it's really almost down at the deck. As a matter of fact, we've actually done deployments in conditions where the barrier was less unstowed. But it was interesting to us that it didn't make it all the way down. So we want to get a full swath from tip to toe to head of the arm to make sure we understand where it's at. There's also some checkouts that we'll be doing. Peter talked about the calibrations. We do some self-checks and checkouts, particularly, I believe, as we speak on Mars right now. There are some checkouts going on the MECA instrument, and I believe we'll be taking some of the surface images by the workspace today as well. Is there anything I missed?
Probably, but I think we're trying to take a multispectral spot of the digging area too. But since we've been here and the team is planning it in Tucson, it's been a little hard to know exactly what they're doing.
And just a quick follow for Peter. You mentioned the release of additional photos on the web. Is that later today or tomorrow? Can you?
Yes, our downlink is later in the day, and the pictures will be coming down with that downlink. As you know, we send up commands in the morning and we send down data in the evening on Martian time. So I think it's, do you know the downlink time is around 5 o'clock?
It's Yeah, I think it's around 5, a little after 5, maybe 6 o'clock.
5 to 6 this afternoon. There should be another downlink, and as many images as we get, we'll be putting them right out into the community.
Okay, let's go ahead with caller Mark Stein from KOLD Tucson on the line. Go ahead.
Yes, this question is for Peter. Peter, with the science portion of the mission starting here at the University of Arizona, how special was it for you, and how great was it for the University of Arizona? Was it that HiRISE took that picture of Phoenix with the parachute?
Well, as you might know, I spent 2 years as the project manager helping to build HiRISE, and I have a great affection for it, although it drove me nuts sometimes. That instrument is really a beautiful piece of engineering, and the scientific products that it is providing for Mars are as good as anything you could have imagined when we started designing this. And so it's just a wonderful thing to me that Alfred McEwen was willing to take a picture of our spacecraft coming down through the surface. It's kind of, how would you say, a collaboration between 2 different groups in the Lunar and Planetary Lab working together. Is just a beautiful thing, from my opinion, and the picture is awesome. So we're now awaiting an image from HiRISE of our spacecraft on the surface, so we know exactly where it is, and we hope to see also the heat shield and the back shell and the parachute. All of those things will be visible, and we just haven't seen them quite yet, but we will. And once we do, I'm pretty sure, because we carpeted this whole area with HiRISE images, that we'll have a before and after picture showing what the site looked like before the lander was there and then after the lander came down. So that should be really spectacular. And wouldn't it be nice to get that tomorrow too? But I can't promise it because we haven't found it yet. And but it's coming.
Okay, we have a couple questions in the front row. We'll get a mic over to you.
Sally Rail with the Planetary Society for Peter. We know that the mission is scheduled for 90 days, 3 months, but we know from the Mars exploration rovers that just because a mission is scheduled for 90 days, it doesn't necessarily last 90 days. How long could Phoenix survive?
Barry has a good way of expressing that.
We're going to operate until Mars freezes over.
Thank you.
Let me give a more detailed answer to that. All vehicles have different limiting resources. On MER, our limiting resources when we were in the design phase was power, and what we figured would be our limiting factor on power was dust accumulation on the solar rays. The reason MER has lasted so long is we didn't levy a requirement on Mars to blow the dust off, but it cooperated for us, and the vehicle's been running and running like the Energizer battery. One thing we cannot count on Mars is for it to change its orbit or stop in its orbit around the sun. And what the limiting factor for Phoenix is going to be is the sun's going to go away. And as we get past 90 sols, right now where we are on the above the Arctic Circle, we have the sun up a full sol, 24.6 hours a day. And so we have lots of energy. But after we get to sol 90, if you look at the curve of the number of hours per sol that the sun is above the horizon, it dips rather radically to the point where it actually, I believe it's in April of next year, goes down for a better part of 3 to 4 months. Sometime before that, however, we will get to what we would call a power negative state, where we're unable to put out enough energy to keep the vehicle alive. That won't be after the sun goes completely below the horizon. We've speculated that that may be 150 to 170 sols away.
Thank you.
Sure.
Go ahead, Emily.
Emily Lochtawala with the Planetary Society. I have a couple of questions relating to power. I'm wondering if you can tell me about current situation with the power on the lander, if it's performing better than expected, same as expected, or if you have any information. Second question is, I'm wondering why the solar panels are flat instead of tilted toward the south as they would be for a polar solar-powered object on Earth.
Well, First of all, I haven't seen the data. What I can tell you is that we did have some indication of what the opacity, which is the amount of sunlight that can actually get to the solar rays, was at landing time. And when we designed the mission, we designed it for a range of optical opacity. And so we were in a very high sunlight regime. I have not seen the data on how much power we're getting out of it, but I assure you it's probably in excess of what we expected on Sol Zero, since we generally are fairly conservative. I haven't seen the data right now, but I know it's above. We can pull that out for you if you like. As far as tilting to the south, I don't know the details, but one thing that I can say is what we didn't have is we didn't have an ability to actuate it. That would add more complication. But keep in mind, this vehicle was designed to be an equatorial mission when it was first designed. So this was not intended to be a polar region that would try to take it into account, the sun being low on the horizon. And that's probably the reason it's the way it is.
Thank you.
Going to the back of the room. Go ahead.
Good morning. I have Gordon Tokumatsu with KNBC. I have one for each of you gentlemen, if I may. First, Mr. Goldstein, you said that you were highly skeptical at first. What was giving you nightmares at this point? At that point, I mean, what was the worst-case scenario in terms of what could go wrong?
Well, I wasn't getting nightmares over it. I was skeptical about the ability to hit the target. I wasn't worried about it. I had no technical objection to taking the image. I was skeptical that they would be able to get it, and I am amazed. I will never be a skeptic on certain individuals again. Obviously, as I called Rob Manning this morning, I told him I'll never object to anything he suggests again. So, well, maybe you're right. It is going too far. Rob, if you're listening to this, take that back. So it wasn't a fear. It was just skepticism on that part.
And Mr. Smith, could you tell us very briefly about the implications of what we find out here and what it means for the future, perhaps habitation of Mars? That's obviously a leap way into the future, but what does it mean, what we find out from this mission?
Well, as we look over this landing site, you see a very flat, kind of barren landscape that it's kind of lumpy. But you have to realize in the winter this is encased in carbon dioxide ice, which may be several feet deep. I mean, it's a completely different landscape in the winter. And so it's gone through these cycles of winter, summer, and while it goes through those cycles, the polar tilt is changing, so the climate changes. And so one thing we found about polar regions on the Earth is that it's a good record keeper of climate change on the Earth. So we wonder if perhaps on Mars we'll find clues as to what the climate has been like in the past by studying various signatures under the surface, from the surface down. Our mission is all about digging. So we're not roving over the surface, we're digging into the surface. And that's where the science discoveries are likely to be made. So the pictures may look a little bleak, but the science can be absolutely fascinating. The other thing that we've learned about polar regions on the Earth is that there's a long record of organic materials that's preserved in the ice, just as you preserve organics in the freezer in your kitchen. That's the place that you can go back even 1 million, 2 million years and bring signatures of organisms back to back for analysis. That's where they are. You won't find in the equatorial region when something dies there, it's completely regenerated back into its basic elements. It's not preserved. It's part of the life cycle. So we're wondering on Mars, is there any indication that organic materials are preserved in this ice? And probably the organic materials would come from asteroids and comets that have hit the surface of Mars over the last many eons, let's say. And if it's preserved there, then I think that changes the way that we're going to be exploring Mars. We're going to be going where ice is accessible, or digging deep enough that we can get to ice, because that's going to be, in my opinion, the next way to explore Mars, if you want to look at modern Mars.
Okay, we're going to take a lot of questions on this side of the room. Thanks for being patient. We're starting here with Mark Crow.
It's Mark Carew from the Houston Chronicle, and I have a question and a follow. The first one is what you know about the health of the arm at this point, and if you know when you may move it.
Well, one thing we've learned in testing the arm is you want to be moving it when it's above a certain temperature. I don't remember the exact temperature, but you want to move it at the warm time of day because there's a lot of greases and things inside of these gear trains that you want to be sure you have the best chance of moving without snagging it. So we'll be checking the temperatures today, and I think the plan is to move it tomorrow once we know that the temperatures are above that lower limit. And there's every indication that they will be. So probably be tomorrow by the time we move the arm.
Thank you. I had another question about the first dig or first sample analysis. Can you sort of give the context of how far this site is from the lander and sort of what the objective of that particular sample analysis will be, and some sense of the sort of time it takes to carefully look at what you're doing and make the analysis?
Is that a 5-part question?
I'm sorry, it's a complicated machine. I appreciate that.
Well, I think you're asking about how we're going to take samples from the soil and analyze them. The arm is 7.7 feet long, and so depending on the height of the deck above the surface, and we think the legs have crushed about 4 inches. We can tell by the stereo image that we've taken that how far away the foot is. So it looks like the legs have crushed about 4 inches. So that's typically where we expect it to be. So we should be reaching out almost, say, 6 feet away from the lander deck, and we can subtend an arc between the two solar arrays. Obviously, we can't go through the solar arrays. So that is our digging area. It's about 3 or 4 feet by 2 or 3 feet. It's 12, 15 square feet. And the science team will be choosing the most scientifically promising sites out in this area to dig a trench down to the ice. And we will be examining layer by layer as we get down from the surface to the ice, looking for transitions in the minerals and the chemicals that make up these soils. And what we're hoping to find, and the reason we brought these instruments with us, is that there will be indications in the soil that the ice is melted. At warmer climate periods on Mars, if the ice melts, the water actually changes the properties of the soil, and it'll change mineral structures. It'll put salts into the soil because it'll leach them out of the rocks, put them into the soil. You might actually find layers. Could be textural layers like pebbles and so forth. So we'll be looking at all these structures in the soil to tell if the ice is melted. And then we'll also be sampling the ice itself, seeing if that's a place where the organic materials have been preserved or not. And this is going to take us several months, so it'll be through the summer, so you have to learn some patience here. We're not going to have instant results on these big questions.
Okay, Ivan, go ahead, and then we'll go to John Johnson after that.
Sure. Ivan Semenek with New Scientist. A couple questions for Peter. First, it seems like you are surprised that the polygons are smaller than you expected, if I've got that right?
Yeah, well, we thought we were seeing them from the high-rise images in space, and we did a distribution of their sizes, and now that we've landed there, they seem smaller.
So, and what might that mean, or what could be the explanation for that?
Well, remember, we've only seen this one slit. Now, we may turn the other way, and they're all bigger, so I hesitate to make too many conclusions from this one view of Mars, but I think it just means that there's polygons within polygons within polygons, and it's at different scales. There's probably at different climate times there might have been big polygons, and at others there were smaller polygons, and it just may go back and forth over time.
And just a quick follow-up, you talked about how active the surface is, and could you give us a picture of what that activity means? You know, how does one of these troughs dig itself? How does it happen?
Well, as the temperature gets cold, of course, the ice can change temperature. As the ice gets cold, it tends to contract a little bit, and it'll form very narrow cracks, and then the sand falls into those cracks, and so now you see a little depression on the surface where the sand has fallen into a crack, and so you don't actually see the crack itself. You see the sand has a little furrow in it from losing some material into the crack. And then in the summer, when the ice tries to expand back where it was, the crack's filled with sand. It can't do that, and it tends to buckle a little bit. So you see these kind of mounded structures with the cracks around them.
Thanks.
Okay, we'll go to John Johnson, and then we have another call from Tucson. Go ahead, John.
John Johnson, Los Angeles Times. Is there, I mean, if you had your druthers, would you like to get into one of those cracks? I mean, is that a place where you'd like to go with the arm? And I have a follow-up from that.
We're hoping that we find a trough and a polygon center within reach. That would be great, because we'd really like to know the process that's forming these polygonal structures. There's several different ways it can happen on the Earth, and knowing how it happens on Mars would be very important to our science.
And the follow-up, given the perturbation of the soil by the footpad there, can you characterize today how you feel about getting, how easy it will be to dig into that soil?
Well, clearly the footpad has modified the soil. You could see a slide mark. You could see some clods have been dug up, and there's a little bit of an opening into the soil. I think we won't have any trouble at all from what I see. I'm very confident we can dig in this material.
Okay, we have a call from Tucson. Please go ahead.
Sure, this question is for Peter. With last night's successful landing, what does this mean for the future of exploration and space travel, and for the University of Arizona's involvement in future missions?
Yes. About 4 in the morning I was thinking about this. No. It's a good question for you, Mike Meyer.
The answer is the University of Arizona.
Well, the university kind of went a little bit out on a limb by providing us an entire building for our operations center. And knowing that the mission really has an end date on it, and preparing this huge operations center for one mission was a very bold move on the university's part. And they did it because they felt like this was the beginning of a long-term kind of contract between the university and the space business, and we wanted to be a major player. So the university is really putting the stake in the ground here and saying we're ready to be actively involved in space missions, and we'll start with Phoenix and then we'll move on to many other missions. Now, what those missions might be, I couldn't tell you today, but our fervent hope is that the university will, that this is just the beginning for us.
Okay, let me try to, okay, Henry, please go ahead, and then we'll take one more question on this side.
Henry Bortman, Astrobiology Magazine for Peter. I know it's really early in the mission, but I'm going to ask you to get into the science a little bit. You talked about active soil, you've talked about the polygons having cracks, you've talked about the size of them. There's been discussion in the background material about different cycles ranging anywhere from seasonal to 1 million years, which in a geologist's mind are basically the same thing. And I'm wondering if you could kind of put that together and also give us an idea. You said there are different ways that these polygons could form. What are you actually looking for, and what's it going to tell you? And can you give us an A-B?
There are different types of troughs that surround the polygonal features. In the wetter areas in the Arctic, which is definitely much more moist than the Martian terrain, what happens is when these cracks form, the melted ice runs into the cracks and refreezes. So you end up getting what are called ice wedges. And if you were to dig a cross-section through these, you would see a big wedge of ice that is formed in these troughs. And in drier climates, like the Antarctica, there's not enough meltwater to go into the cracks, and maybe it never melts, and you find sand wedges instead of ice wedges. So if we were to find ice wedges in these cracks, that would mean that there was a very wet environment at some time in the past in this region, and that would be a major discovery for our science team, because it's liquid water that we're looking for. We know there's ice there. That's already been discovered and published 6 years ago, but does the ice melt? That's the real question that is driving our science.
And could I follow up on that? My understanding was that on Mars, ice tends not to melt but to sublime. So what's the mechanism by which the ice could melt, remain liquid long enough to have these kind of rock-water interactions?
Well, this is the beauty of our landing site. We have landed where the pressure is high enough because we're at a low enough Martian altitude that we're above the triple point of water. So what you have to do is get the temperature above freezing. And then you could have liquid water. It's not going to be stable for long term. I mean, water on the Earth isn't stable for long term, and tomorrow this will be gone. So, and not because I drink it, but but because it'll evaporate. So, even on Mars, if water were stable at above freezing temperatures, it could melt some of the ice and run into the cracks, for instance, and you could form ice wedges, and that's something that's helped us choose this landing site as opposed to waiting and going to the southern pole, where the altitude is much higher, the pressure is lower, and it's not even possible to have liquid water in this current epoch on Mars.
Okay, we have one more question over here, and then we'll see if we can get one.
I think this is for Barry. Maybe I missed it last night. Given that you must, I'm sorry, Kelly BD Sky and Telescope, you must have shadows that have told you what the azimuth is, and you said it was a range last night. You now know what that is, and also, though you don't have MET data yet, what is the expected temperature range at the site that you have day and night?
Well, I did mention yesterday that we had missed our planned azimuth by 0.6 degrees, which was just phenomenal. Excuse me. I think I have the nominal azimuth here, if I can look it up. Yeah, we're at, well, aligned directly east-west. So the bottom line is we're off by 0.6 degrees from nominal, and that's pretty darn good. Average temperature in Mars at this region we had assumed would be about -40, and as Peter said, we're reading about -33 Celsius, and so it's a little bit warmer than we expected. But as you might imagine, depending on where you are and the shadows closer to the ground, we might go as low as -100 Celsius, yes.
Okay, we're going to take last question here in the front row. Go ahead.
Emily Lochtawala from the Planetary Society. Looking at the photo taken by HiRISE, the parachute doesn't look quite as inflated as it does in the simulations. I'm wondering if we're seeing it just at the point of inflation or if there's some squidding or something.
Oh, gosh. I can tell you I don't believe there's any squidding. Dirty word around here, squidding, by the way. We don't like parachutes to squid. I'm not going to speculate on that. As I said, we're going to get the data, we're going to reconstruct EDL and try to determine where we were in the timeline when the image was taken. Keep in mind, you're looking at the vehicle from very far away at probably a very steep angle, so I won't make any judgment about the size of the parachute in that image.
Thank you.
Okay, well, that will conclude today's briefing on the Mars Phoenix lander mission, and please do check the website frequently. As they mentioned, we will have new images coming down this evening, and they will go to the website. You can go to www.nasa.gov/Phoenix. We will have another update on the mission for you tomorrow at 2 p.m. Eastern, 11 a.m. Pacific. Please join us then. Thank you.
For more on this mission, we talked with Doug McQuistion. He explained why mission planners decided to land the Phoenix so close to the Martian North Pole.
A lot of the water vapor and the water content that's left at Mars that we're aware of is captured in those poles. So just like climate change on Earth can be captured over the centuries in the polar ice, we expect the same situation to be present on Mars. We're also hoping that we find the traces of organic materials, and we're hoping that we find evidence that periodically that ice actually turns to liquid water, very important and necessary in the ability to sustain life, which is what we hope we can prove that there used to be or is currently habitable areas on Mars.
All right, that was Doug McQuistion, obviously looking for life on Mars. He's the director of NASA's exploration program. I want to show you some interesting pictures here to give you some perspective on exactly where the Phoenix lander is. You can see the North Pole, right? This part. Now, the little arrow there is pointing right to where the lander is located. So it's very close to that pole. Now, as we heard, it's searching for water. Let's take a look at the H2o readings on Mars. Now, you see those darker bluish and purple areas that are in that? Well, that is where they expect to see the highest concentration. And that, of course, is why the lander was sent so close to the pole, even though it's going to turn into an ice cube and end the project after just 3 months. Now, you can read all about the Mars mission on our CNN.com webpage. You can also see the latest photos of the red planet taken by the camera mounted on the Phoenix spacecraft and learn what others are saying about this mission on our sci-tech blogs. For all of this and a whole lot more, just go to CNN.com/space. They're spending a lot of money to get in all this information. We're going to follow these pictures as they come out, little bit by little bit. As soon as they develop them, we're going to show you some so we can tell how things are going out on the red planet.
Das ist ein Meilenstein, so die NASA, denn jetzt sieht man nicht nur die Gesteinsbrocken und Bröckchen gestochen scharf. Das ist ja nur der erste Teil der Mission. Phoenix soll nach außerirdischen Lebensspuren fahnden, nach Wasser zum Beispiel. Damit wäre dann die Erde nicht mehr der einzige uns bekannte Ort des Lebens im Weltraum. Da, wo Phoenix jetzt ist es nachts so um -85 Grad kalt und tagsüber 20 Grad. Claudia Kleinert, was wird uns morgen hier auf der Erde erwarten?
Also bei uns wird es morgen an die 30 Grad heißen. Was ganz spannend ist, auf dem Mars gibt es richtiges Wetter. Da gibt es Sandstürme und da gibt es beispielsweise auch Wolken, wie so Schleierwolken, wie so Zirren. Und Sand bzw. Sand in der Luft bekommen wir morgen auch, nämlich ganz feinen Sahara-Staub, auch wenn der in Nordrhein-Westfalen nicht so großartig zu spüren sein wird. Vielleicht im äußersten Süden merkt man, dass die Autos noch so ein bisschen weiß bestäubt sind bzw. gelblich bestäubt. An sich...
Die Planetensonde Phoenix hat ihre weite Reise von der Erde zum Nachbarn auf der Umlaufbahn 1 weiter draußen geschafft und ist auf dem Mars gelandet. Fernsteuerung über eine Entfernung, für die selbst das Licht- und Funksignale eine Viertelstunde brauchen. Das war und ist eine Meisterleistung, berichtet Hildegard Wert.
Für Horst-Uwe Keller war es eine aufregende Nacht, denn mit der NASA-Sonde Phoenix ist eine seiner weltberühmten Spezialkameras auf dem Mars gelandet. Sie sitzt am Roboterarm und soll später, wenn Phoenix zu baggern beginnt, direkt in die Schaufel gucken. Die Landung war ein Höllentrip und eine Zitterpartie für alle, die seit Jahren an diesem Projekt gearbeitet haben. Nach einer Reise von 680 Millionen Kilometern geht es in den letzten 7 Minuten um alles oder nichts. Beim Flug zum Mars sind schon viele Sonden verloren gegangen. Aber Phoenix kommt durch. Das erste Foto nach der Landung sieht eintönig aus, aber genau so hatten sich die Forscher die Landestelle gewünscht. Flach und mit möglichst wenig Steinen. Unter der körnigen Oberfläche vermuten sie große Mengen Eis. Wie die Suche funktioniert, zeigt uns Keller in seinem Mars-Sandkasten. Bis zu 60 cm tief gräbt sich der Roboterarm in den Boden. Die Schaufel schiebt den Aushub dicht vor die Kamera. Dabei werden Details sichtbar, die kleiner sind als der Durchmesser eines menschlichen Haars. Kellers Trick?
Dass das die erste Kamera ist, die einen variablen Fokus hat, wo man also vom Makroeinstellung 1:1 bis zum unendlichen Aufnahmen machen kann. Und das ist das zum ersten Mal, dass man das im Weltraum einsetzt.
Mit seinem Team baut Horst-Uwe Keller die raffiniertesten Kameras dieses Sonnensystems. Sie trotzen den extremsten Temperaturen und der brutalen Strahlung. Jede ist ein Einzelstück, maßgeschneidert für die Anforderungen der jeweiligen Mission. Mit 6 verschiedenen Kameras ist Keller zurzeit im Sonnensystem unterwegs und seit heute auch auf dem Mars.
Ich glaube, ein großer Erfolg wäre, wenn wir wirklich das Mischungsverhältnis von Eis und Wasser feststellen können und wenn wir organisches Material fänden an der Stelle. Das wäre schon wichtig, wirklich Wassereis in der Hand zu haben oder in der Schaufel zu haben.
Die Phoenix-Mission soll herausfinden, ob auf dem Mars einmal Leben möglich war und ob noch Spuren davon vorhanden sind. Die Bodenproben werden in einem Ofen verdampft, damit sie ihre Geheimnisse preisgeben. Wegen der großen Entfernung dauert es 17 Minuten, bis die Signale auf der Erde ankommen.
Und dann findet man vielleicht Materialien, die also sagen, ob das Wasser da gestanden hat mal oder ob Lava geflossen ist. Da wissen wir sehr wenig darüber. Und ich glaube, dass da bedeutende Aussagen gemacht werden können.
Auf dem Mars hat gerade der Frühling begonnen. 150 Tage lang wird die Sonne nicht mehr untergehen. Optimale Bedingungen also für die Phoenix-Mission. Mit etwas Glück wissen wir danach mehr.
Und 1983 stellte ein deutscher Astronom fest, dass es auf diesem Planeten Jahreszeiten geben muss. Auf dem Mars ist es die meiste Zeit eisekalt bei Temperaturen bis zu -125 Grad. Nur in ganz kurzen Phasen wärmt er sich auf, dann bis auf 35 Grad. Kein geeignetes Klima vielleicht für kleine grüne Männchen, aber die Mission, die heute den Mars mit einer Bilderbuchlandung erreicht hat, ist ihrem Ziel, dort Leben zu finden, doch wieder ein Stückchen näher gekommen. Ina Ruck.
Ihre Chancen standen 50-50, rein statistisch. Und bei der NASA wussten sie das, denn immerhin die Hälfte aller Mars-Landeversuche der letzten Jahrzehnte ist gescheitert. Diesmal sollte es bitte klappen. Und zwar möglichst so reibungslos und so schön wie in der Computersimulation. Da tritt die Mars-Sonde Phoenix zunächst bei großer Hitzeentwicklung in die Atmosphäre ein. Dann bremst sie elegant ab, fährt die Beine aus und landet sanft in der bislang unerkundeten Nordpolregion des Planeten. Das Ende einer Reise, die fast 10 Monate gedauert hat. Exakt um 1:38 Uhr sollte Phoenix aufsetzen. Und dann gespanntes Warten, denn es dauerte noch mal geschlagene 16 Minuten, bis das Landesignal die Erde erreicht hatte. Und die ersten Fotos kamen gleich hinterher, noch in Schwarz-Weiß. Zunächst Kontrollbilder von der Sonde selbst, zum Beweis, dass nichts kaputt gegangen ist bei der Landung. Auch Mars-Oberfläche war zu sehen, Begeisterung bei den Forschern, auch wenn sie hundemüde waren. Perfekter, als man sich es hätte erträumen können, sagt der Projektleiter. Phoenix ist exakt da gelandet, wo wir wollten. Und wir haben schon die ersten Daten. Sie müssen sich das so vorstellen, es ist, als ob man versucht, einen Golfball mit dem ersten Schlag einzulochen. Aber der Abschlag ist in Washington und das Loch ist 10.000 Meilen entfernt in Australien. Kein schlechter Schuss, oder? Hey, du hast noch was vergessen, sagt der Kollege. Du musst noch sagen, dass das Loch sich auch noch bewegt. Wissenschaftlich verspricht man sich nicht weniger als die Antwort auf die Frage, ob es Leben auf dem Mars gibt. Der Schlüssel liegt im Marsboden, genauer im dort eingeschlossenen Eis. Wenn man feststellen kann, ob dieses Eis regelmäßig auftaut, könnte das bedeuten, dass organisches Leben zumindest denkbar ist. Es geht um Wasser in flüssiger Form, danach suchen wir. Wir wissen, dass es Eis auf dem Mars gibt, aber schmilzt es? Es wäre eine Sensation, wenn wir das herausfinden könnten. Herausfinden soll das die Phoenix-Sonde ganz allein. Das Foto ihrer Landung, aufgenommen von einem der NASA-Mars-Satelliten. 3 Monate lang wird die Suche nach Leben auf dem Mars dauern. Auch deutsche Technik ist dabei, eine Spezialkamera aus Niedersachsen. Phoenix wird Bodenproben nehmen, diese im bordeigenen Labor untersuchen und die Ergebnisse zur Erde funken. Forschungsarbeit, ferngesteuert über Hunderttausende von Kilometern.
Und das war's von uns für heute.
A unique glimpse of another world. These snapshots from space are the first images beamed back from near the Martian North Pole. A dry and stony desert, the landing site for NASA's latest visitor to Mars.
50 meters, standing by for touchdown.
But there were tense moments before touchdown when all they could do was watch and wait.
Touchdown signal detected. Landed it.
And this was the moment they'd been hoping for. Confirmation that the Phoenix spacecraft had landed safely on the surface of the red planet.
We rehearsed over and over again. We rehearsed all the problems, and none of them occurred. It went perfect, just the way we designed it.
After a 9-month journey from Earth, the craft faced a short and perilous descent. This NASA animation shows how Phoenix had to plunge through the Martian atmosphere at more than 12,000 miles an hour. First, a parachute to slow it down, and as the 3-legged lander dropped to the ground, thrusters fired, bringing it to just 5 miles an hour for a soft landing. And just 2 hours later, delight at mission control, as the crucial photographs reveal the craft's solar panels have successfully deployed, the robot's vital power supply. Phoenix is continuing the hunt for evidence of life that began more than 30 years ago with NASA's Viking missions. Successful landings, but no signs of life. More recently, the Spirit rover captured this breathtaking panorama and detected hints that water once flowed here. But several other missions went badly wrong, including Britain's. Here in the Science Museum in London is a model of Britain's own Beagle 2 spacecraft. It was meant to look for life on Mars, but crash-landed on the surface 5 years ago. The mission was a failure.
Now Phoenix will attempt something that no previous craft has tried. It'll dig beneath the barren surface to study the water that's thought to lie frozen underground. Onboard experiments will analyse the samples for any evidence of the chemical building blocks of life. Beneath this dusty, cracked surface could lie the clues to whether life has ever existed somewhere on Mars. Christine McGurty, BBC News.
Even the publicity machine was impressive. Their mission to boldly imagine what the landing would probably look like. The idea was that first a parachute and then thrusters would slow the Mars lander from 12,000 miles per hour to just 5 miles per hour for touchdown.
Atmospheric entry on my mark.
In real life, the team in California called this the 7 minutes of terror.
3, 2, 1, mark. Touchdown signal detected. Landing sequence initiated.
Phoenix took off on the 4th of August last year. It has taken 10 months to travel the 422 million miles to Mars. There have now been 39 missions to Mars. Only 17 of them have succeeded.
It's like trying to hit a hole-in-one, but you tee off in Washington and you hit the ball 10,000 miles and you score a hole-in-one in Sydney, Australia. So, Charles, not a bad shot.
You have to remember that hole is moving.
So what next? Well, like a lonely tourist, Phoenix started with a few photographs of itself to give the team a visual check on its solar panels and other equipment. 2 more spacecraft remain in orbit around the planet to relay these images. Then it sent back a snap of the view. Not so impressive until you remember where it is.
Now we're going to get a little closer, and you can see lots of pebbles and obviously soil, and we can see there are differences in color in the soil. If you look in the upper left of that image, it's a little bit of a darker streak. Over the next few days, we'll be getting the whole scene filled in. We've only looked at one little sliver of the Martian surface, but it's exactly what we wanted, and I couldn't be more pleased. This is a scientist's dream.
Phoenix will now unleash an array of testing kit. An 8-foot-long arm will take soil samples and dig for ice below the Martian surface. The samples can then be analysed for the carbon-based compounds, which would be the likely prerequisites of life on Mars. The mission is expected to come to an end in the Martian winter, when there's no longer enough sun to power Phoenix and the Arctic region where it landed freezes over.
And eventually, our lander will be completely entombed in ice.
Carl Dinnan reporting there. Well, for more on the Phoenix lander, we're joined from Washington by Keith Cowing. He's the editor of NASAWatch.com. Thank you very much indeed for joining us. A happy day for anybody who's interested in NASA and its attempts to land on Mars.
Oh, absolutely. Spectacular images, and I just can't wait to see the data come back.
Let me ask you what we might expect from the data in just a moment. But first of all, the 7 minutes of terror. I mean, why is there such a high failure rate for missions to Mars?
Well, NASA loves to come up with these things like you just heard, hitting a golf ball from here to Sydney. Or it is very difficult to do. I mean, we're talking about sending a very complex piece of machinery at immense speeds and then slowing it down very fast and dropping it exactly where you want to put it and not hitting a boulder. And by the way, it's happening automatically, and due to the distances, you won't even know that it's going to happen until after it's happened. So it's quite a prescription for nail biting.
I can imagine, but how much of it is down to luck, even if all the figures are and data are in and correct?
Well, what did Woody Allen say? Once is luck, twice is good planning. I mean, there's always an element of luck in this.
Let me ask you about the data that we've seen so far. It's very early days. I know that this mission really is primarily concerned with finding water under Mars's surface. Why, for the uninitiated among us, are scientists so convinced that there is water in Mars?
Well, there's something very interesting. Last night when I watched the pictures come down, and I put this up on my website at NASAWatch.com, I've spent some time up in Devon Island, which is near the North Pole, and it's an island that NASA and other space agencies send people to because it's a lot like Mars. Well, I saw this first picture come down, and you're scrolling through it right now, and no kidding, these two places look awfully alike. The polygonal shapes on the ground, which is result of the way that ice works beneath the ground, freezing and thawing and so forth. And based on what we know about such, and there you can see it right now, as you see these locations on Earth, we know there's life in that soil. And again, this is Mars and this is Earth, the two different planets, but there are similarities. So just based on that alone, it's tantalizing. And as a biologist, I'm just wiggling in my chair waiting for them to start doing these tests.
How long will these tests take to complete? And, you know, in general, how would you describe the kind of tests that are going to take place?
Well, there's no actual test that per se is looking specifically for life, but what they're looking for are organic compounds, a variety of other materials that will let you sort of infer by the fact that there's carbon compounds there. Well, how do they get there? If the little mineral shapes are clays or so forth, they can interpolate that maybe there was flowing water there. They can tell by the mineral content what sort of water was flowing there. So you can narrow in on the conditions that might have created life. And, you know, you don't know. You might find fossils if there was life. But again, until we start these tests, but within the next few weeks, we're going to know some interesting things about this part of Mars.
I hate to play devil's advocate here, but what could go wrong in terms of this mission, in terms of taking the photographs and sending back the data to Earth?
Well, I think they've pretty much got through the scary stuff. The fact that the spacecraft landed, did precisely what it's supposed to do, exactly on time, in even many cases ahead of time, I think bodes well. I mean, hardware is hardware, but unlike the rovers who, by having dust storms clean off their solar panels and so forth, this spacecraft has a finite life. It is eventually going to freeze over. So they've designed it to be very hardy, but they're focused on a very 90-day window of time, and they've got their experiments set such that they can answer their questions in that 90 days.
And the 90 days of information that comes back, I mean, how much information does that give you and your fellow scientists and journalists and bloggers to work with?
Well, it's like peeling away the layers of an onion, just seeing the surface as we did right off the bat. We don't know how these features were formed, but we had a good idea. But the fact that we can just see them, and as we move forward and we start scraping the ground and digging into the ground and pulling material out and putting it into these things, bit by bit we'll get closer and closer to a much better understanding of exactly what this part of Mars is like and whether there might have been life or if the conditions may have been present at some point where life could have arisen.
When you talk about fossils and the possibility of what may be coming back in the next few weeks, I mean, essentially you are saying it is life as we know it, be it on Earth or Mars. It's the same organic compounds.
Well, you know, life as we know it, and life as we know it keeps changing on Earth. When I went to college initially, the notion of finding life forms in hot volcanic vents miles beneath the ocean was thought to be nonsense, and now it's a regularly, you know, announced finding that they found yet another kind. There are similarities between Earth and Mars as planets, where if it arose on Earth, maybe it arose in a similar way in Mars. Maybe life was blasted from one planet to another or back and forth. We don't know. But we're going to learn a lot more in the next few weeks about some of these basic ideas.
Great stuff. Look forward to talking to you then at some point. Thank you very much indeed, Keith Gowing, editor of NASAWatch.com, for joining us from DC.
My pleasure.
Welcome. In legend, the phoenix is a bird that rises from the ashes. In scientific reality today, NASA's Phoenix spacecraft survived a fiery fall through the Martian atmosphere and landed with a soft bump near the planet's north pole. It was the end of a 423 million mile, 9-month journey. It's the beginning of a mission that scientists hope will further unlock the secrets of the red planet. Our science correspondent Christine McGurty has this report.
A unique glimpse of another world. This postcard from space shows the northern Arctic region of Mars, photographed in close-up for the first time. A dry, stony desert is the landing site for NASA's latest visitor to our neighbouring planet.
50 meters, standing by for touchdown.
But there were tense moments before touchdown when all they could do was watch and wait.
Touchdown signal detected. Landed it.
And this was the moment they'd been hoping for. Confirmation that the Phoenix spacecraft had landed safely on the surface of the red planet.
This is our beginning. I mean, it's like without the launch, you have no mission. Without the landing, you have no mission. Now we have a mission. It's up to us to make it something wonderful.
After a 9-month journey from Earth, the craft faced a short and perilous descent. This NASA animation shows how Phoenix had to plunge through the Martian atmosphere at more than 12,000 miles an hour. First, a parachute to slow it down, and as the 3-legged lander dropped to the ground, thrusters fired, bringing it to just 5 miles an hour for a soft landing. And just 2 hours later, delight at mission control as the crucial photographs reveal the craft's solar panels have successfully deployed the robot's vital power supply. Phoenix is continuing the hunt for evidence of life that began more than 30 years ago with NASA's Viking missions. Successful landings, but no signs of life. More recently, the Spirit rover captured this breathtaking panorama and detected hints that water once flowed here. But several other missions went badly wrong, including Britain's. Here in the Science Museum in London is a model of Britain's own Beagle 2 spacecraft. It was meant to look for life on Mars, but crash-landed on the surface 5 years ago. The mission was a failure. Now Phoenix will attempt something that no previous craft has tried. It'll dig beneath the barren surface to study the water that's thought to lie frozen underground. Onboard experiments will analyse the samples for any evidence of the chemical building blocks of life. Beneath this dusty, cracked surface could lie the clues to whether life has ever existed somewhere on Mars. Christine McGurty, BBC News.
Well, for more on the mission to Mars, I spoke just a brief time ago with Dr. Tom Pike from Imperial College in London. He's part of the team working on the Phoenix lander. Dr. Pike, I've read that you've spent more than 10 years of your life on this particular project. How did you feel when Phoenix touched down and everything seemed to be okay?
Oh, it was extraordinary. Having waited so long, and our hearts were really in our mouths right at the last moment when we saw the countdown on the radar altimeter. And I was thinking, this is just coming in too fast. And then the retro rockets kicked in. As we had this commentary second by second as the progress of Phoenix as it was coming in, we saw it slow down and then touch down, and the room erupted. So many people have spent so many years on this mission.
It is astonishing, 423 million miles, give or take a bit, I guess. And how do you ensure that something like this passes off so successfully as this appears to have done?
There's a lot of testing. I think that the difference between this time around, where we had success, and the last time when we were trying to get to the South Pole of Mars in 1999, the real difference is that we tested and we tested. And so the confidence that we had that although we were going back to the retro rockets last used in Viking over 30 years ago, the confidence was high. We really wanted to get down without using the airbags, using this more graceful way of getting onto the surface so that we know that we're in a good orientation to start digging as soon as possible.
And international collaboration as well, I presume, because your team is from Imperial College London. NASA's been getting the headlines on this, but presumably a lot of people from all around the world working on this.
Yeah, we've colleagues from Switzerland, from Germany, working on various aspects of the microscope station that I'm working on. And we've got a real international team from Denmark as well working with us. So there's a lot of international collaborations going on in this mission, with of course NASA taking the lead.
Good afternoon and welcome to NASA's Jet Propulsion Laboratory. I'm Veronica McGregor. We're here again for another news update on the Mars Phoenix lander mission. And today we have something a little different for you. We will have panelists both here in Pasadena answering questions, and then we have panelists also in Tucson to take those questions. On Mars, by the way, right now it is Sol 2, and if you were where Phoenix is right now, it would be about 2:10 in the afternoon. So to give us an update on what is going on Mars today, we have with us Phuc Le. He's the manager of the Mars Exploration Program here at the Jet Propulsion Laboratory. And Brent Portok, the navigation team chief, also from the Jet Propulsion Laboratory. I'm sorry, Brian. Alfred McEwen, the principal investigator for the HiRISE instrument, the camera on the Mars Reconnaissance Orbiter. And Peter Smith, the principal investigator for the Phoenix Mars lander from the University of Arizona in Tucson. And we're going to begin with Phuc Le.
It's still morning here, so I'll say good morning. As you can see, I'm not Barry Goldstein, so you'll have a poor substitute for Barry here with me. I talked to Barry yesterday. He had not been home for a number of days, and he was very tired, so we had a handshake deal, so I'm substituting for him. The first thing I'd like to report to you is basically what we had tried to plan for what to do with Phoenix on this second day on Mars. There is, however, a transient event that has occurred on the UHF radio on the Mars Reconnaissance Orbiter. And when this transient event occurred, the Mars Reconnaissance Orbiter is programmed to turn that radio off. This occurred sometime this morning, and we were going to uplink the set of events that Phoenix will be doing, and because of that transient event, those uplinks were not accomplished. Phoenix is healthy. Everything is fine. Is running out a sequence of commands that it has pre-stored on board. The MRO team is in the process of analyzing what had happened. They are also in the next several hours trying to turn that UHF radio back on, and hopefully everything would be just back to normal. What I'd like to do now, however, is to show you some of the pictures we have on the robotic arm. As Barry have talked to you earlier, the robotic arms has a biobarrier that covers it to prevent contamination from Earth when we launch there. And I'd like to show you a more complete picture of the robotic arm that Phoenix has acquired, and also show you where the biobarrier is today. And then I'll make some more comments after that. Can I have the first video? So this is the looking through the eyes of the stereo imager onto the robotic arm, and you can see how it's rested, and you can see this mosaic picture of the whole robotic arm. Everything looks nominal to us. We love to see hardware that we last saw on Earth, now that is resting peacefully on Mars. And one thing that was mentioned previously was this biobarrier, which, if you look at this picture, is a set of folded structure to the kind of the lower on the southwest quadrant. If you look at the whole thing, and can I have the next still picture? May I? This is the picture of this region surrounding the elbow. On Sol 0, as was reported to you, when after we landed, there were a number of critical deployments, including the solar arrays, including the masts that hold up the camera and so on. One of them is also the deployment of this biobarrier. And on Sol 0, you can see how much it has pulled open. We pull a pin, and there is a spring that drags this out and open this thing. And you can see that it was not 100% open. We reported back to you at that time that this is not any major concern to us, because we believe that there is enough clearance. We should be able to move the arm anyway, so it was not a major concern. But we also wanted to let the system go through the first day on Mars, because during the warmer time of the day, it's believed that some of this material that make up the biobarrier would warm up. They'll relax a little bit, and the spring would pull it farther. Can I go back to my still? And you can see on Sol 1, I hope you can see the way that the stuff has been pulled further down. So the clearance is now even better. Okay. So among the first thing that we will plan to do in the next set of events would be to start deploying this arm. So with that, I'd like to turn over to Brian.
Hello, I'm pleased to announce that we really confirmed the location of Phoenix on the surface. And this is really a culmination of an extraordinary effort by the team. And in the past few days, the navigation team has received a tremendous amount of recognition for getting or helping to get the Phoenix spacecraft to the right spot on the surface. And I'd just like to point out that without all the other systems, it really is impossible just for the navigation team to do it. The two key components really, one is the spacecraft. The spacecraft has to perform as predicted in order for us to do our job. and it did so in an excellent fashion. We did, excuse me, we did 4 TCMs in order to get to the correct entry point on Mars. Each TCM, the spacecraft had to turn on its engines in the right direction. And really thank you to the ACS team and the rest of the spacecraft team for executing those maneuvers so well. Secondly, the Deep Space Operations Network provides us with our tracking data. We use Doppler data, spacecraft ranging data, and something called Delta VLBI. That's an extraordinary powerful data type and really made our job possible. And I just want to say thanks to the DSN, specifically the Delta VLBI team. Okay, so there are 3 ways that we use to figure out the location of the lander on the surface. Now, the first way is just to use all the data before EDL, figure out where the spacecraft is going to enter in the atmosphere, and then propagate it to the ground and estimate, where's the possible landing area where it could end up. The second way is the spacecraft actually measures on its way through the atmosphere how far it's traveling, and therefore when it lands can send back basically its estimated position of where it landed on the surface. And we had that immediately after landing, and Barry Goldstein reported that at that day's press conference. Since that time, we've actually used measurements from Mars Odyssey and Mars Reconnaissance Orbiter, measurements of the lander that is similar to the global positioning system here on Earth. It's not exactly the same, but it's very similar, and it's analogous to your navigation system in your car figuring out where you are at any particular time and telling you to turn left or right. Well, we've done the figuring out where the lander is. So if we go to the first image, please. What you see here are 2 ellipses. There's actually 3 ellipses on here, but there's a green one that's probably difficult to see at the moment. The blue ellipse is the estimate of the position or the landing area where we could have been prior to EDL. So that's why it's the largest ellipse, because it includes the effects that take place through the atmosphere of EDL. The red ellipse and the red center, the blue ellipse is 60 kilometers by 20 kilometers. The red ellipse is the estimate of the position that the spacecraft sent back to the Earth through telemetry using the measurements it took during EDL. So that ellipse is a 20-kilometer diameter circle, actually, on this image. Now, if we were to zoom in, I'm not sure if we have the zooming capability or not. There's actually a green point on this image that is the navigation estimate of the landing location. It's totally consistent with all the other estimates. It's about a kilometer different from the red center you see on this image. So the general results of where we landed was 22 kilometers downrange from the pre-EDL estimate. And through a lot of hard work and some good fortune, this is only 7 kilometers away from the TCM-5 target. So we're happy to say that we really landed in the spot that the scientists were looking for. And now we'll just move on to Alfred McEwen, who will really walk you through the final confirmation of the landing location.
Okay, and as Brian just said, we're going to go to Arizona right now, Tucson, Arizona, and Alfred, go ahead.
Hello, thank you, Brian. I'm going to tell you about the view of Phoenix from the MRO spacecraft and the HiRISE telescope on MRO. And I'm going to talk about pieces of just 2 images. The first, if I could have the first slide, is the same image that Barry showed yesterday morning, only in our exuberance over seeing the parachute, we just zoomed in on the parachute. And then later, we zoomed out and were astonished to see the setting of this crater, informally called Heimdall Crater, behind Phoenix as it descends on its parachute. So that's what's shown here, and it looks like Phoenix is dropping right down into the steep rocky slope of this crater. It isn't really. It's actually about 20 kilometers in front of this crater. It just happened to be right in the line of sight between MRO and this crater. There was Phoenix. So it's an optical illusion that's hard to understand because we're looking through a very large focal length telescope. And Phoenix, this really gives you an idea of how small Phoenix is in relation to Mars and this one 10-kilometer diameter crater. We've also done some improved processing of the parachute image, and we can see the gap in the disk gap band parachute. If you probably can't see it here on the TV screen, but on the web that will be shown. And there's some interesting dynamics of the parachute here. This opened about 20. We took this picture about 20 seconds after the parachute first opened. So then we took some images of Phoenix on the ground, and thanks to Brian and others, their work in locating it, we were able to hit Phoenix on the ground in our first 2 tries. The first one was 11 hours after EDL, and the next one was 22 hours. That image just came in last night, and Eric Eliason and others at our operations center in the wee hours in the morning here were processing that image and have it ready in time for us here today. So if I go to the next slide, we'll show you what Phoenix and other hardware, associated hardware, looks like on the ground. Well, here's a little video first, right? Here's the MRO spacecraft flying over with a simulated field of view of the high-rise camera. Zoom in on the surface, as shown here, and there is the image in color. In our second image, the knowledge of the location was so accurate that we could get it in our narrow color swath in the center. And there are 3 pieces of hardware that we should be looking for: the lander itself, the parachute attached to the back shell, and the heat shield, or its impact mark. And we see 3 things in this image which correspond to exactly, if I could have the next slide, I think there are some labels on this image. That's exactly what we see here. Well, we'll just zoom in here. At the bottom of that image is the parachute attached to the back shell. This is rotated so that north is down. So that's the back shell at the bottom and the bright parachute at top. And in the full-res image, you can actually see the stripes on the parachute here. You can see a hint of the strings connecting the two. And there's a dark area, which is where the dust was disturbed as this thing came to rest on the surface. On the next view, we'll take a look at the heat shield, I believe. And we believe there's 2 dark spots here. The one on the lower left, we believe, is the heat shield itself, or the marking made by the heat shield, and the one on the right is a bounce mark, or it could be the other way around. We're not sure exactly, but it's the marks made by the heat shield, and it bounced. This thing was dropped and just free-falled when it was released from the parachute. And the next slide shows the lander itself. There it is in color. It stands out remarkably well against dark red Mars. You see the 2 solar rays perfectly. We took this image to make sure, in case we were needed to verify that the solar rays were open. That wasn't the case. But you see those very well. And the bright spot in the middle is some specular reflections on parts of the lander, so it appears off-center compared to the solar rays. So we're thrilled with these images. And now for a view from the ground, here's Peter.
Good morning. We're so pleased last night to be able to get some more images around our landing site. And if I can show the first graphic, we're looking now to the south, and this will be the first of a series of mosaics that will take us all the way around the 360 degrees surrounding the lander. But first we're looking to the south. And as we look into the terrain, we see the sparsely rocky surface, and we see the mounds and the troughs that represent the polar terrain on Mars. And we see a nice rock up close that has a very interesting shape, and we can zoom into the distance, and as we look straight south, just as Alfred has shown in his picture from the orbiter, we see the back shell and the parachute. But because there's so few pixels involved here, and that back shell parachute combination is I think 300 meters away, and so we don't get a lot of detail there. We just see a bright area. So we'll take a higher resolution picture later on and see if we can distinguish between the parachute and the back shell. Also in that image, if you look towards the horizon, you will see there's some low hills. Those are about 9 miles away, and they're just a little rise in the terrain that marks the valley that we've landed in. So about 9 miles away, and we can see it fairly clearly. That means there's not too much dust in the atmosphere. It's a very clear day on Mars. Our next image is even more exciting because this is where we're going to be doing our science for the next 3 months. This is our digging area where the robotic arm is able to reach and actually interact with the soil. Now, looking through the camera in this animation, and now we overlay the actual pictures of the digging area. And these pictures show that there's only a few rocks in the digging area, which is great news to me because the arm is not built really to handle a very rocky terrain. So we have lots of areas that we can dig in. You'll notice some of the rocks look like they've actually been shifted and moved a little bit. This must be because of the thrusters as we came down. They exert quite a force, and so they're certainly able to move some of the rocks. All of this is prime digging area that you're seeing here. You see some little streaks that probably came from the thrusters as we came down to the surface. And now look at this shift in the shadow of our camera. That's a self-portrait. Now those two mass pictures don't line up because the mosaic is taken over a period of time and the sun is moving in the sky. So the shadows have shifted between the taking of the upper picture and the lower picture, and that's why it doesn't line up. But this is a place we're going to get to know very well over the next 3 months. We are fairly sure, both from Alfred's pictures and from some preliminary elevation maps we've made, that we'll be able to get into one of the troughs between the polygons, and that has the science team quite excited to be able to look at the difference between the underlying surface and ice in the trough area and then in the middle of one of the polygons that we've seen. Now, I also have the opportunity to give a weather report from the surface. Our Canadian team has done an excellent job of giving us temperature, pressure, and wind data. And tomorrow they'll be taking their first measurements of the cloud heights. But today we're just able to give a brief weather report, and we'll hear more about the weather tomorrow. The temperatures go from minus 30 centigrade to minus 80 centigrade, and this would be between minus 22 degrees Fahrenheit and minus 112 degrees Fahrenheit. So rather cold. It's a chilly, particularly at night here. Not as cold as it would get if the sun set all the way. Remember, we're above the Arctic Circle, and the sun has not set yet for us. It won't set until sometime in August. And so the temperatures are milder than they could be in other places. We notice the pressure is about 8 millibars. Surface pressure on the Earth near the sea level is about 1,000 millibars, so we're just a little less than 1% the surface pressure of the Earth. And we're noticing the winds are about 20 miles an hour coming from the northeast. So that's today's weather report, and we'll be having the weather reports regularly throughout the mission. And finally, we have a picture that we released yesterday, and if we could show that picture, it's our Memorial Weekend picture. It shows the American flag, and it also shows our mini DVD that was put onto the deck and was provided by the Planetary Society, and contains 250,000 names of interested people who really wanted to support our mission and get their names on Mars. And it also has a library of Mars-relevant books that are inside of this DVD. This DVD will be there for a very long period of time. And on the DVD it says, "Astronauts, please take this with you." And that's for future astronauts that may come to the polar region of Mars. Who knows how far in the future? Maybe in the next century, we hope. Maybe 5,000 years from now, maybe 100,000 years from now. But someday, somebody will come and take that DVD and be able to read the books in our little library. So we're very proud to be making such progress. It's only been a day and a half since we've landed. We're already getting a good sense of what the space is around our lander. We've got wonderful pictures from Alfred's high-rise telescope. Brian Portak has located us on the surface with his navigation, and we're really feeling very positive about this mission and can't wait to start interacting with the soil and doing our scientific investigations. Back to you, Veronica.
All right, thank you, Peter. Okay, so what we need all of you to help us out with is we're going to take questions, and please wait for the microphone to come to you and give us your name and affiliation, and then please tell us if you are directing your question toward a panelist in Tucson or someone here at JPL. Just give us the name so that we can bring them up for you. So where am I going to start? First question. I'm just going to go where the microphone's closest, Leo, and I'll come to you next, but let's start right here.
Henry Bortman, Astrobiology Magazine. For Brian, I think, maybe someone else will want to answer. There was a 7-second delay in the opening of the parachute that was mentioned early on, and we haven't gotten an explanation for that yet. Can you tell us what progress has been made on analyzing that and when we can expect to hear?
That's maybe a better question for Fu.
Okay, I'll give it a try. The short answer is we're just at a very early phase. It's going to take us a number of weeks, months, to try to analyze all this EDL telemetry that has been played back through Odyssey, through MRO, and through Mars Express. So we're at a very early phase to try to understand the issue that you mentioned.
Okay, Leo, go ahead.
Question for Peter and one for Dr. Lee as well. The trough that you see, I have to confess that when I looked at the pictures of the digging area, I had trouble making out a trough, a border to a polygon. You're satisfied that you can see one, or can you give us a hint where you see something that, as I say, I can't see? And then I had a question for Dr. Lee as well, who gave us a wonderful tour of the MSL facility yesterday. What does Brian's targeting tell you about confidence in MSL, because you need to be within, I think, 20 kilometers of your targeted area of interest. So is there something that we know today about your capacity that we didn't know yesterday?
All right, should we start with the question here at JPL? Yes, Fook, why don't you go ahead with that, and then we'll go to Tucson and Peter Smith.
Yes, that's a very good question. As I mentioned to some of you, every time we don't have that many times to try to enter and descend and land on Mars. So every time we do that, we try to capture those engineering information to teach us how we can do better next time. And in fact, MSL is indeed trying to land in a smaller ellipse. MSL itself has a slightly different design features. It has a guided entry. You know, it actually fires through jets to try to position itself down, to try to narrow down this landing ellipse. But nonetheless, the data that we get back from Phoenix would teach us a lot more. And you know, we're confident MSL would do well as well.
Okay, we're going to go to Peter Smith now to answer the other question. Go ahead, Peter.
Well, you don't have all the information you need to see the trough. The 3D pictures that we're using here show you the actual terrain elevations, and we haven't found a way to release those yet so that they can be interpreted by the general public, but we'll be doing that today or tomorrow. So towards the left side of this mosaic, there is definitely a dip compared to the right side. So it looks very much like one of the trough boundaries, and in fact, you can see it from Alfred's latest image, the one that shows the color, the blue lander. And that image shows a depression moving away, what looks like a depression moving away from the lander, just at the same place we see a dip in our elevation models. So all of us are fairly confident that in this type of terrain, a dip like that has to be a trough. I mean, what else would it be in this kind of terrain? So we are definitely going to try and do a profile across the trough and into the center portion of these mounds that are surrounded by the troughs.
Craig, go ahead.
Good morning. It's Craig Colt with Aviation Week, and I believe both of these for Fook Lee. What commands were you trying to upload to have Phoenix do that didn't make it due to the UHF issue? And secondly, you showed the Planetary Society disc there. Is there a microphone embedded in Marty ever going to be able to be turned on?
Let me answer the first question. The command sequence that was being planned to be sent by MRO is the sequence of activities that Phoenix would do in SALT number 2. Okay, so that is the one that we have missed, and it has altered the schedule of when we can do it. As I said earlier, MRO is right in the middle of trying to understand what happened and turn that radio back on. Insofar as a microphone, I know the answer, but I'd like to turn it over to Peter to answer that part.
It's true that Marty has a microphone, and it's potentially usable. However, it was not designed to operate on the surface. It was designed to operate during the descent. And it's also not part of our mission success plan. Really, we have our primary science to do first. But as with you and many other people, we would all love to hear some noises from the surface of Mars. That would be a first. And we will be working on a plan later in the summer to try and see if the microphone is still operating and if it's possible for us to turn it on.
Okay, David Perlman.
Okay, I'm Dave Perlman from the San Francisco Chronicle. Just two questions for Arizona. One is, can you give us an idea of the distance between high-rise and the images that were taken of the back shell and, of course, that beautiful blue image of Phoenix itself with its outspread solar panels? How far away was high-rise, if you have any idea?
Okay, if the question is how far away was high-rise itself, it was about 300 kilometers above the surface when the image was taken. If you're asking me how far apart are the objects on the surface, the parachute in the back shell landed about 300 meters south of the lander, and the heat shield is about 200 meters, a little bit off to the east, southeast of the lander.
Okay, thanks. And the other question for Peter, do you still have any fixed date or approximate day on which you're going to start digging?
Well, as you heard from Fook, we have a small delay here. We were hoping to unstow the arm, or at least go through the first steps of unstowing the arm today, and that'll have to be delayed till tomorrow. So we were hoping that we would have on Sol 5, 6, 7, somewhere in there, the first touch of the surface, and then the first practice scoopful and dump activity, and then towards the end of the week, maybe Sol 9, 10, 11, somewhere at that time frame, we would be actually delivering the first sample to the TIGA instrument. But we certainly would have to add an extra day because of the electric problem we're having with the orbiter.
Okay, I'm going to take one out over here.
Todd Halverson of Florida Today for Fuqli. What is left on the day one command sequence to accomplish? And I have a follow-up.
Yes, this I heard from Barry. And the run-out sequence, basically, they're going to continue to take some temperature measurements and some of the stereo imagery that will be, being taken, and those data will be relayed back once, in the next pass that we go over the Phoenix site.
And just to follow, can you still communicate with Phoenix through the Mars Odyssey spacecraft, and would it be possible to uplink the SALT 2 commands through that relay?
Yeah, that's a very good question. The short answer is yes. The mission is designed to operate both with the Odyssey and MRO UHF radios. There's also, we use the term contingency plan. In case one of the radio is not working, we'll operate with the other one. So right now, it's a little too early for us to switch to that mode. We're going to try to see if we can turn the radio on MRO back on, and then we'll go back to the normal process that we go through. But the Odyssey radio is working, and we can certainly use it.
Okay, we're going to Steve Futterman next. And then
I guess maybe Arizona may be here, but can you give us more simplistic version of what's happening with this radio problem? What is not working? How critical is it? Would it affect the potential accomplishments of this mission if it was continued to cause problems?
Peter, you want to address that, or you want me to address that?
I prefer if you addressed it, Fook. I only just found out about this problem.
Okay. Okay, I'll try. I'll give you my best. again, as I said, there is a set of commands planned, through the several days that we have. There is also a backup set of plan that in case one of the radio is not available, the team is right in the middle of trying to decide what to do. I would call it sequence deferred, but not deleted. Okay, so we'll have to wait and see how that process goes. The hope clearly is that the MRO radio will turn back on and we'll just go back to normal. And if not, then we'll have to ask Odyssey to do double duty.
But potentially, let's in a worst case scenario with the MRO radio not coming back on, would that affect the goals of the whole mission?
I do not think so. Okay, we would just again have to ask Odyssey to work harder.
Oh, Emily, go next. Thanks.
Emily Lakdawala from the Planetary Society. I have one question for Peter and one question for Alfred. Peter, if you are within reach of one of the troughs, I'm wondering if you would dig 2 trenches, one in the center and one in the trough, or if you would just scrape one and dig a deeper trench in the center, if you could comment about that. And for Alfred, I was just wondering if you could comment on the high-rise team's plans for supporting the Phoenix mission with more images.
Well, as far as digging a trench, the first thing we're noticing is there is an opportunity to do a profile from an interior of the mounded structure down into the trough. And so we might try and do both in one trench. This is really early in our planning stages, and we haven't gotten an accurate enough elevation model yet that we're all comfortable with, that we're willing to make a final choice by any means. But it looks like we have lots of good opportunities here to either dig only in trenches, in troughs, and only into the polygonal centers. And so, or even to do a transition. So there's just a wonderful kind of buffet of opportunities here in front of us, and we're just anxious to get more data and make our determination. We also haven't quite filled out the panorama behind the digging area, and that means we can't see how these features are moving, how they move into the distance. Are they really part of an array of polygonal structures, or is it just a unique thing right next to us? We really want to get the whole context before we make those kind of decisions.
Okay, next question over here. Oh, I'm sorry. Did I interrupt? There was another question there to answer.
Yes, I believe that was addressed to me. And Emily, high-rise is available to support Phoenix in any way that's useful. We do have another image planned in +5 sols. And this will be actually our best image yet of the surface because it's more directly overhead. And then we're going to acquire stereo images in order to get a topographic map of the larger region around the lander, larger than what Phoenix can directly see to measure the topography. And we can monitor the surface to see if anything changes from the wind or frost later in the season and so forth. Whatever is helpful, we'll do it.
Okay, now we'll go to the next question. Go ahead.
Okay, this is Ivan Semenek with New Scientist magazine. This is with a question for Peter Smith. Peter, I'm just wondering if you've had a chance to, or if you have the information yet, to compare the polygons on the north side with the south side. Yesterday it was clear that the north polygons were a little on the small side. Do they look that way on the south, or do you have a good sense of that? That's the first question. I have a follow-up.
Well, at first look, that looks very similar to me. I don't see a big discrepancy from north to south, and I think looking at Alfred's picture from high-rise, you see kind of a self-similar terrain all around the lander. So I don't think we're going to find we landed on the border between 2 different types of terrain. I think it's all the same kind of location. And fortunately, I think our digging area is very typical of this landscape, so I expect we're in just an ideal place.
That's great. And the follow-up is, I think, for anyone who could address this. On day 1, so we now see the back shell quite clearly to the south of the lander, but on day 1 we had that curious object in the northern view, the monolith or the polar bear or whatever, or abandoned snowmobile or whatever it was. So any thoughts yet on, or perhaps from MRO on what that might be?
I can take that. All I can say is that from high-rise, we don't see anything unusual in that direction. My first guess would be that it's something like a cosmic ray hit, an artifact in the image, because it's very linear, but we haven't seen anything from orbit in any event that's unusual to the north of the lander.
Thank you.
Okay, next question. We'll go across the aisle here.
Henry Bortman, Astrobiology Magazine. One for Fook, and then I think one for Peter. Let me just get clear on the communications issue. This is a problem with MRO communicating with Phoenix, but not MRO communicating with Earth. Is that right?
That's exactly right. MRO communicates with Earth using what we call X-bands, and it has some big antenna to communicate to Earth. The whole MRO spacecraft is working fine. The transient event occurred with the UHF radio that MRO used to communicate with Phoenix, either uplink or downlink. It's that radio that had the transient event.
And to follow up on that, if that's not repaired today, then does that mean that there also will not be an uplink of additional data and images tonight?
I don't know the answer. The team is working on how to react to this. Again, whether we should activate more of Odyssey or not. So we have a lot of resources in our hands, but let's also wait and see how MRO, whether it can wake up the radio again or not.
Okay, and for Peter, does this problem with the radio mean that there's a delay in completing the panorama around the spacecraft, or does Phoenix already have the commands needed to accomplish that?
Well, my understanding is we have a run-out sequence today, a run-out sequence being what the spacecraft does if it does not receive a command in the morning that tells it what to do. So it'll be taking more of the panorama and some weather data. My understanding was, and I may be incorrect, is that there will not be an ability to downlink this today, and we'll have to wait till tomorrow.
But it will finish out the panorama and the run-out sequence if it doesn't get additional commands?
I don't think so. I think it'll probably do the same thing again tomorrow if it doesn't get more commands. So we're going to use the Odyssey spacecraft tomorrow to uplink our commands, and that should work just fine.
Yeah, maybe I can add to it. In fact, part of the command that was planned to send up from MRO today include part 2 of the pan. So that would be deferred.
Okay, one more question on this side. Go ahead.
Todd Halverson in Florida Today again. I'm just trying to understand the communication strategy that you have with Mars Reconnaissance Orbiter and Mars Odyssey. Is MRO the prime for uplinking commands, or is it just that it was in the right orbit to do that job today? Could you kind of explain the strategy?
Yes. We use basically 2 players in this process, both Odyssey and MRO. We use them equally. We use them, they complement each other. Okay, so there is, as I said, there are backup plans if one of them has problems, and we use the other one, and we have to work them harder. But right now, bear with us. Let's see if we can wake up the MRO radio.
Just a quick follow, if I could. I'm still not sure I understand. If Mars Odyssey is available, why not just uplink the Day 2 commands through Mars Odyssey? Is it the orbit that MRO's in that made it prime today for uplinking, or?
Well, as you know, all our commands and playbacks are sequenced ahead of time. Okay, so when we got the surprise this morning, we could not just 1 minute later and say, oh, let's turn over to Odyssey. So we have to wait. And the plan is now to wait and see what we can do with MRO. And we might use MRO again today if it turns up.
Some clarification, things I'm not quite sure about. On the links between Phoenix and MRO and then Phoenix and Odyssey, are those equal as far as the width and the speed that you will have if they both work? Is one, it sort of sounds like what Todd was asking, is one preferred over the other? Would one be higher quality than the other?
No, they are similar. The 2 radios have been sent up in different times, but the capabilities are very similar. So that's not the issue. The issue is, again, kind of working out what is the best time to utilize both spacecrafts.
And secondly, there had been communication link earlier?
Correct.
Okay, so it was working, now it's not working.
Correct. And in fact, you probably know that during EDL, we used the MRO to capture the EDL telemetry in this open loop recording, and that worked perfectly fine. Everybody walked out of the room when we were at the event, but I was still in the room, and you can see the MRO spectrum, and it looks, as you know, perfect.
And lastly, the problem, do we know if the problem is with Phoenix or with MRO?
We know for sure it's with MRO. Again, let me be very specific. We know that it is with the UHF radio of MRO. The rest of MRO is doing fine.
So everything with Phoenix, though, is working fine. You've been able to, this problem has nothing to do with Phoenix itself?
Not that we are aware of, nothing.
Okay.
Yeah.
Okay, we're going to take one more question here in the room, and then we're going to go to a phone call. Go ahead, Leo.
Leo Enright from Irish Television again for Peter Smith. You were talking about hills 9 miles away and a valley. Could you talk a little bit about what you know about the context in which you've landed? I mean, a valley, is it a wide valley? You know, a little bit about the geology, if you feel comfortable with that. And I heard some chatter about some people describing this as a mesa. Is that excessive? It's not that big, presumably. What sort of height are we talking about for these hills?
Well, I can tell you what I know. We landed in a valley that's about 30 miles wide. Because we'd kind of colored it green as an indication of the rock counts in the valley, we were calling it Green Valley for a long time. It's not a river valley or anything like that, and it's certainly not green in its appearance from images, but it's safe, and that's why it's green. The hills that we're seeing 9 miles to the south, we knew would be there, and they're about 250 meters high, very similar to 250 yards high. So they're just low hills. I think mesa is not a bad word for them. I don't know if they're formed in the same way as mesas we're used to, but probably not. But they've certainly been eroded features, and you could see various hummocky structures in the right side of the image I showed. So the terrain we've actually landed on has more to do with the crater that Alfred showed. That what we call the Heimdall Crater is only, I think, what was it?
20 kilometers.
20 kilometers away. That's 12 miles away. And we're still in the ejecta blanket. In other words, the material that we're landing on was once inside of that crater. And that was a good thing for us because the crater apparently has very few rocks associated with it, and therefore the ejecta that came out was a nice rockless terrain. And we know from the Odyssey orbiter that there's a lot of ice in this area. So we expect as we dig through what looks like a very barren, dry desert soil, we will actually get to an icy region.
Okay, we're going to take a phone call from Eric Hand of Nature Magazine, and the question is directed to Phuc Lee.
Hi, Phuc. This is Eric Hand with Nature. Quick question. You said that the UHF failure on MRO was caused by a transient event. What sort of things can cause a transient event like this? And how often has this happened in the past with UHF radios on this and other orbiters?
First, let me comment on, you use the word failure. I try not to use that word. There was a transient event. It could possibly be caused by cosmic ray or other events that has the radio encountered. And the second part of your question is, have we seen this on MRO? The answer is no. This is the first time we've seen such an event.
But you haven't been using the UHF radio very much.
We have been using it over 100 times or so. We've been practicing. We've been using it to practice how we do EDL and all that stuff. So we've turned it on. So it's been, I don't know the exact number, but perhaps over 100 times, thereabout.
Okay, but a simple explanation for the sort of event that can cause this transient event is something like some blast of electromagnetic radiation.
It's probably not electromagnetic radiation, but some sort of a high-speed cosmic ray particle that hit some part of the. I'm conjecturing, so I shouldn't really conjecture, but that is a possibility.
Okay, thank you.
Do we have any more questions here in the room? Okay, Ivan, let's hold on 1 second, we'll get the microphone to you.
This is just a quick follow-up to the previous question for Fuqli. Can you determine if the problem with the radio is in the receiving end or the transmitting end of the radio?
We don't know. Okay. Yeah, and the team is in the process of analyzing that.
Thank you.
Okay, we have one more question over on this side of the room.
Yeah, Todd Halverson of Florida Today again. For Fuqli, what is the recovery plan right now with the UHF radio on MRO, and when is the next time you anticipate attempting to uplink a command sequence through that spacecraft?
The spacecraft team, the MRO spacecraft team, is in the process of turning the radio on as we speak, and we should be able to have some information an hour or two from now, and we'll see what it does. And we'll have to then plan our activity following that event and understanding how the radio is behaving with this, with the team trying to turn it on.
Okay, I think we're done with all the questions here, so that will conclude our news briefing today for the Mars Phoenix mission.